For about 150 years now, the scientists believe that right around where we are located in the solar system, there is a very unusual formation known as the Gould's Belt. Now essentially what this belt represents is a kind of a link between different stellar nurseries where various stars, including stars like our own sun, are formed. And it also includes a collection of bright and really massive stars that essentially form a kind of a projection you can see across the night skies. A lot of various stellar nurseries where stars are made and also various molecular clouds are all part of this unusual formation, and they kind of seem to be connected to some extent as well. Some of the more famous nurseries, including the Orion's Nebula, are also part of this, and many scientists even believe that maybe this belt is actually technically a ring forming a kind of a circle around the location where we are. And although the origin of Gould's Belt was not particularly well known to us, the scientists thought that maybe it was created by some kind of a really massive chunk of dark matter that kind of shot through our galaxy, creating this kind of a circular formation in the middle. The ring itself is actually named after this guy right here. This is Benjamin Gould, who, along with another really famous astronomer, William Herschel, was able to observe all of these formations and identify the connection between these molecular clouds. But for over a century now, this is basically all we knew about this formation. There were some speculations that of course it's a ring and possibly even some other unusual formation, and there were also speculations that various gas clouds form a kind of a ring around the galaxy and are also possibly connected as well. But all of this was of course just suggestions. There were no actual physical proof of anything. And that's of course until very recently, when the paper from Harvard University kind of changed all of this and presented us with a completely new understanding of what's really happening here, and also creating an amazing map that we've never had before. And all of this is thanks to the ESA's Gaia telescope that was able to map nearly 2 billion stars around us with extremely precise and very accurate motion parameters for every star, allowing us to see the distances and of course the actual velocity of various objects located around the solar system. So because of this data we were able to create a lot of new maps, including this one right here. And you can actually explore this map by yourself in the link in the description below. It's kind of difficult to see the credit here, but these are the people responsible for creating this, and you can also find the major scientists behind the study right here in the paper in the description. So you can kind of see that the sun is right here, and then there is this unusual line-like formation if you were to look at the galaxy from the top. But as soon as you start looking at all of this from the side, you'll notice that it's actually not a line at all. As a matter of fact, they refer to it as the Radcliffe wave because it does seem to have wave-like properties. The properties that become a lot more apparent as you start analyzing all of these formations. And by the way, the previously mentioned Gould's Belt is also part of this unusual wave. So it turns out that it's not a belt at all. Instead, it's a wave-like formation that connects all of these stellar nurseries and a lot of various molecular clouds all together, forming a region that's nearly 3 million masses of the sun in total. And each of these representations you see, each of these red little circles, that's essentially a major formation in the night skies, such as a really large molecular cloud, or some sort of a stellar nursery that we've known about for a very long time. And because this is technically a wave, it can also be described using amplitude and period. And apparently the period here is around 6,000 or even more than 6,000 light years across, while the amplitude is about 500 light years. In other words, this is a really tremendously large structure. But at the moment, we have no idea how to explain any of this, or how this wave was formed, or more importantly, what sort of an event would be responsible for creating this wave-like formation. Now, the best explanation is of course, once again, some sort of a large chunk of dark matter that may have either passed through or even landed in our galaxy, creating this kind of a ripple, almost like a ripple in a pond if you drop a rock into it. Now, because this is a wave-like formation, there's going to be a lot of interest in trying to figure out how this occurred and if there are other similar formations somewhere out there in the universe, or more specifically, I guess, in our own galaxy. But from what we understand, our sun does interact with this structure. It passes through these locations and actually does sort of move up and down on this wave. And so, for example, 13 million years ago, it passed through the Orion, but it might actually pass through one of these locations again approximately 13 million years later. suggesting that our sun and our solar system is actually kind of surfing this wave. It's going up and down, and it's moving along with a lot of other stars in this region. And the current location of our sun, which is here, is approximately 500 light years away from the center of the wave, while the total length of the discovered wave so far is about 9,000 light years long, which technically would make it the largest structure, coherent structure in the galaxy so far. The width here is roughly around 400 light years, so it's a huge formation, and it's definitely one of the more mysterious but also more interesting formations in the nearby space. And what's even more interesting is that the actual wave, as you can see here, kind of goes above the galactic disk and also below it. So in a sense, it's creating a ripple that crosses the galactic disk in a way that we can't really explain right now. So basically, there's a part of this structure that sticks out above and a part of it that sticks out below the galactic disk itself. And one of the links that I posted in the description below includes this very accurate map of all of the molecular clouds present in this unusual wave, including of course some of the more famous regions, such as various clouds right here, part of the Orion constellation. And one of the major reasons why it's only recently that we're able to create these unusual and very exciting maps is not only because of the collection of data, but because of the visualization techniques that have advanced so much in the last few decades. Now we don't just have numbers in tables and in essentially difficult to understand and comprehend graphs. Now, however, we have 3D maps that allow us to connect the dots and see the patterns that were kind of invisible to us previously. But at the moment, this is actually the first such publication, so there's going to be a lot of more follow-up studies that will probably explore this even more, and most importantly discover even more detail about how large this wave possibly goes and whether it connects the entire galaxy in some way. This beautiful picture created by Jakub Glos of UCLA kind of shows us what these objects might look like, at least what we think they look like. But what exactly are they? Well, if you look at the center of our galaxy, you'll discover a really extreme environment. There's a lot of things happening here, a lot of them are extremely energetic, and a lot of life would probably not survive here for a very long time. Even though simulations like this present this region as somewhat similar to what we see around us in where our sun is, in reality the energies here are so dramatic and everything is so extremely chaotic that most planets and most stars very likely get destroyed really quickly. And the closer to the central black hole you get, the more dramatic things get. So a few years ago, the scientists observed a passage of what's known as G2 cloud very close to the black hole that resulted in the formation of unusual gas that very likely fell into the black hole. But we didn't really know until now what exactly is happening here. And more specifically, we had no idea where this cloud came from and if there are other similar clouds around the black hole. We actually knew about at least one other cloud known as G1, but it didn't really have such a dramatic shift as we've observed with the G2 cloud that came very close to the black hole, probably the closest so far. And so it took a few years for the scientists to try to figure out what exactly this is and how this may have been created, and more importantly, if there are other similar objects in this region. And as you can probably tell from the title, there are. There are at least 6 now. The scientists from UCLA discovered at least 4 more of these G clouds and were actually able to identify their peculiar features and explain how they may have formed and why they exist in this region. And the major feature of all of these objects is that they tend to stretch out and become a lot more longer, losing a lot of mass as they get closer to the black hole, while as they move away they become compact again and resemble star-like objects. And this is what makes them so unique and so unusual and very different from anything else in this region. And to try to understand all of this, we have to also understand that there are a lot more stars and a lot more material in this region. As a matter of fact, the average density in this region is about 1 billion times larger than it is where we're located. In other words, this is a tremendously hectic environment. And because of this, there's a lot of different stars, and some of these stars might come as binaries. In other words, stars that come as a pair and orbit around one another, which actually represents a lot of different stars out there. The nearby Alpha Centauri is actually a binary star. There are 2 objects in the system. But one thing we know about binaries is that if you place them around a much larger and much more gravitationally potent object, they will eventually start acting a little bit strange. So here's an example. Let's take a star and place it in orbit around the black hole. Notice how its orbit is relatively circular, even though in reality it would still be kind of hectic. But now, what if I turn this star into a binary system? Basically, I place another object in orbit around the star. Well, because of the dramatic tidal effects and a lot of gravitational power that this black hole possesses, these stars will no longer be attached to each other, and eventually they'll probably either fly apart or might end up combining into one. And this combination of two stars will actually result in the formation of a somewhat exotic object. Now here, I think if I actually leave them running, they'll probably just create a supernova, but that's not what we're looking for. We're looking for a kind of an intermediary object, basically a massive amount of gas that's not necessarily a star because it never really gets to form into a spherical object, and is not a cloud either. So it's kind of like an in-between state. It's a cloud and a star at the same time. When it's closer to the black hole, when it's approaching its so-called periastron or the closest part of the orbit, it will eventually get stretched and turn into a very long, dusty object. But then, as it moves away from the black hole, it very likely will start condensing again and form into more of a star-like object. But because its orbit probably takes anywhere from a few decades to maybe a few hundred years or maybe a few thousand years, it never truly gets to solidify into a single piece or an object that can survive for much longer when it comes so close to the black hole. And this, in the essence, is what these G objects are. The scientists behind this paper believe that they originally were binary objects, binary stars. And eventually, through the interaction with the black hole, they kind of stretched, they started to become a lot more unstable and became these very unusual, permanent, stretchy objects. Basically, not really clouds, not really stars, but a bit of both. So they do possess cloud-like shapes and possibly have a lot of cloud-like features, but in the middle they do have these solid objects that kind of possess a lot of mass that eventually pull all of the material back in, creating a star-like object when it's farther away from the black hole. And even though these objects kind of look like a gas cloud, they for the most part behave like stars, and actually remain star-like for most of their orbit. Their orbits can be anywhere from 100 to a few thousand years, and most of this time they do behave like typical stars. Now you might have seen a video I made previously a few months ago about the flares in the middle of our galaxy coming from the supermassive black hole in the center, and these flares are still unknown. Back in August, our black hole essentially became extremely bright for a little bit and then started to dim once again, and the scientists believe that there is a possibility that G objects are responsible for these effects. Basically, as the sum of the material falls into the black hole, it will create these unusual flaring effects. So it's possible that what we're observing is the eventual interaction between Sagittarius A star, the supermassive black hole in the middle, and the G objects that pass there every few hundreds or thousands of years. And even though G2 object came really close to the black hole, a lot of other G objects never really come that close, but nevertheless possess very similar features. They get stretched out a little bit and then become a lot more compact when they're farther away from the black hole. So all 6 objects discovered so far seem to possess very similar properties, making them an actual object that's different from typical stars, binary stars, or any other objects we normally are familiar with. From what the scientists observed so far, they seem to be going from in between these really stretched and distorted objects when they come really close to the black hole to looking like normal typical stars when they're much farther away. And this is what makes them so unique. They are very dynamic and they do change in time. And because things are really far away here, this is about 26,000 light years away from our solar system, it's going to be really difficult to try to identify how they formed, what other effects they have on other stars and the black hole itself, and most importantly, if they can create effects that would be so dramatic that it could somehow affect our solar system and our planet. Now, that's probably unlikely, but we still need to study them in a little bit more detail. And when it comes to star mergers, today we believe that a typical star merger should take about 1 million years to complete. So if a binary star approaches the black hole and its orbit is only a few thousand years, it's never truly going to combine into a single star and will always remain as a kind of a binary mixture, and this is what we believe is happening here. And since our galaxy in general has so many different binary stars, and at the same time since it's quite possible for many binary stars to combine into one star, this could be an explanation to many different other mysteries we're observing around the galaxy that we still can't really explain. So for example, Certain stars out there, like the so-called oldest star in the universe, might have been a result of a very unusual binary combination. Basically, when two stars join together and mix their material, they'll eventually turn into something completely different, something that we wouldn't be able to explain right away unless we knew that this is exactly what happened. In other words, by using binary stars and by using the basically joining of two binary stars into one, we could maybe explain a lot of other mysteries that we're not really clear about just yet. But more importantly, in regards to this study, we now understand that this particular simulation created by ASO a few years ago might not really be that accurate. It seems that the gas itself did not stretch as much as is presented in this video. As a matter of fact, it seems that only the outside part of the gas was stretched, but the inner part of the object remained as a solid part, as a kind of a star-like object. In other words, once again, resembling something similar to what you see in this beautiful illustration. Some of the projections here are formed by the outer gas and some of this will end up in the black hole, but the vast majority of mass here, including the inner part, will still remain as a kind of a star-like object, very likely still producing energy and a lot of light similar to a typical star. And of course, what's kept it all together is this inner mass, this stellar object on the inside, which all of the G objects seem to possess. And so the next question now becomes, are we going to be able to find these objects elsewhere in the galaxy or in the universe? Or is this uniquely only the object you can find close to supermassive black holes? Would we ever be able to find a very similar object somewhere else? Now, this is something we're probably not going to be able to answer for a few years, but I guess you never know. So all of this started only about 13 years ago. In 2007, we accidentally discovered what's known as the Lorimer signal, or the Lorimer burst, which was this unusual radio burst, very short burst detected by this wonderful person, Duncan Lorimer, who essentially discovered them while looking for pulsars. And since 2007, we've actually detected quite a lot of them. Now we've been detecting them pretty much every single week, allowing us to sort of realize that these are really prominent events, really common phenomena that are happening everywhere around us, around our universe. And if you still have no idea what FRBs are, well, essentially they're just very short radio bursts, but extremely powerful radio bursts that can travel across the entire universe. So something really powerful produces them. And even though the first assumption would probably be aliens, in reality these bursts are too random and, well, they do appear extremely natural, as if something natural produced them, but something very powerful. And we've actually had a few speculations, a few, I guess you can call them culprits, that could have caused these bursts, but nothing concrete until now. So there's this really famous website that a lot of astronomers use. It's called Astronomer's Telegram, and it's essentially a website to post all of the updates, all of the recent discoveries, and essentially whatever else unusual stuff that's going on around the universe. For example, when we discover something unusual, like the interstellar comet Borisov, you will probably find all of the information here because the actual discoverer will post it on the Astronomer's Telegram. And this is exactly what happened recently, when the scientists posted the detection from the famous Canadian telescope known as CHIME. Now this is essentially a telescope made specifically for studying FRBs, and it's been operational for roughly around 2.5 years now. Pretty much all of the recent FRB detections, even the more unusual ones, have been actually discovered by CHIME. Here's actually what it looks like in daylight. And so its main goal is to help us understand what these FRBs are, but we didn't really expect to discover the possible answers so soon, even though we were hoping to. And it looks like the possible origin of this particular FRB that we just detected may have been what we always expected it to be: a magnetar, an extremely unusual and very powerful type of a neutron star. And generally speaking, there are already a lot of different mysteries that have actually been solved by identifying certain pulsars or certain neutron stars. And this time it seems like maybe it's no different. Okay, but what are neutron stars? Very quickly, well, they're remnants. They're basically leftovers of a very large star that went supernova, but couldn't really produce a black hole. Instead, it left this. This object is really small. It's only about 12 kilometers or about 8 miles in radius, and that right there in the background, that's basically Earth in comparison. So these objects are really dense. They're also pretty small compared to some of the other stellar objects, but they possess a lot of power, and they also usually spin really fast. In some cases, these objects also produce these pulses that you see right here, and this is when we refer to them as pulsars. But sometimes these objects can become even more extreme, and we don't really know why just yet. And when they become more extreme, they become what's known as a magnetar, which in a nutshell is a neutron star, but is also an extremely magnetic object. It's literally the most powerful magnet in the universe. So powerful, as a matter of fact, that if you were to actually come within, I guess, this distance, a few hundred kilometers away from the magnetar, the actual magnetic field would now cause a lot of the electrons inside your body to start changing shapes and to basically be stripped from the atoms themselves. You would most likely almost instantly die. You would just perish without even realizing. And also the radiation here is pretty high as well, which altogether makes this a pretty unfriendly place to be. But anyway, so magnetars have been sort of responsible for a lot of different effects around the universe, and most recently another paper actually explored the idea of the most powerful, most luminous supernova known as superluminous supernova as being originated by magnetars as well. So basically they're sort of like the tricksters of the universe. They seem to cause a lot of different things that cause a lot of problems for astronomers in not being able to understand them. But this time we got a little bit lucky, because as Chime was looking at this particular spot in the night skies, sort of from the side vision, it was able to see another FRB incoming. But around the same time, a completely different telescope known as SWIFT, that's responsible for looking for different gamma ray explosions around the universe, was able to detect gamma rays coming from pretty much exactly the same spot as this FRB. And interestingly, this particular gamma ray burst came from a very well-known magnetar located inside the Milky Way galaxy, around 30,000 light years away from us. So essentially this allowed us to do two things. First of all, discover an FRB inside the Milky Way, and also at the same time find the origin of the FRB by looking at this location with a different telescope and realizing it probably came from exactly the same source. And not surprisingly, this object now has its own Wikipedia entry, and this will probably expand over the next few months as we learn more and more about it. So it seems that this is definitely an unusual type of magnetar, or basically an unusual type of a neutron star. We don't really know what's different about it just yet, but the fact that we were able to detect an FRB and detect a gamma ray source from it as well implies that we may have actually had our theories correct after all. It's very likely that FRBs are indeed formed by magnetars or unusual neutron stars. And remember, since all of the previous FRBs were extragalactic, basically they came from other galaxies around us, this is a huge discovery. This is basically, assuming of course all of this is correct and it does check out with all of the other studies that are going to be coming out in the next few weeks, this means that FRBs are just as ubiquitous as we thought originally. In other words, they seem to be produced everywhere around the universe, and they're a lot more typical than we originally thought. Although at the same time, the fact that they are produced by neutron stars, or magnetars more specifically, does make it a little bit less exciting as an explanation, because a lot of scientists were hoping for something a little bit more exotic. But at the same time, this might be actually an unusual event as well, because this is the first time ever we've officially associated an FRB with a gamma ray burst. This has never been done before, and it actually now raises questions: why is it that none of the other FRBs produced any gamma ray emissions either? So there is still a possibility that maybe this is just one type of unusual FRBs that are produced around the universe. Maybe they all have different origins. We still have a lot of work ahead of us, and we still need to confirm quite a lot about the origin of these unusual phenomena. But thanks to this amazing Canadian telescope, and also thanks to all of the work done by the scientists working with this, we now got a little bit closer to finally solving the mystery of one of the most mysterious phenomena of 21st century, the FRBs. But what exactly is the physical explanation of how these would be formed? Well, there are actually quite a lot of papers that have explored this theoretically, and the idea here is related to what's known as starquakes. NASA has actually captured quite a lot of different starquakes from neutron stars, and the principle here is very similar to what happens on Earth. At some point, the structure of a neutron star becomes a little bit unstable and experiences a kind of a shift in the star crust itself, and as it sort of realigns itself, a huge amount of energy ends up being released and is then seen in gamma rays and looks like also radio waves as FRB. Now, the crust itself only moves by like a fraction of a millimeter, but that's enough to cause the huge amount of energy to be released. Which also obviously leads us to the next question. Even though we've seen so many different so-called starquakes from neutron stars before, why is it that we haven't really seen any FRBs? Maybe we just weren't looking, but also maybe not all of them are created equally. So this also means that there are still quite a lot of questions for us to answer. Well, it should come as no surprise to you that we don't really know what our galaxy really looks like, mostly because we're looking at it from the inside. We've seen a lot of spiral galaxies that we think are possibly similar to the Milky Way, like this one right here, and we've even tried to simulate what this might look like by looking at it from the inside and then trying to basically extrapolate the outside. But so far we're not really sure on the shape, the number of arms, and obviously the actual full size of our galaxy. One of the recent studies from only a year or so ago actually established that our galaxy is very likely at least 120,000 light years in radius, which is practically the double the distance of the original estimate. In other words, even though we thought it looked kind of like this, in reality, it's practically double the size. We've also reanalyzed the mass, and today most scientists believe that Milky Way is probably the largest and the most massive galaxy in the so-called local group. We've always believed that the Andromeda galaxy that you see right here was larger and more massive, but most of the recent observations seem to tell us otherwise, so it does seem like Milky Way is larger and also more massive. But all of these observations are not really accurate, mostly because as of today we haven't really established where to stop measuring the actual edge of the galaxy. In other words, how do we actually establish where the galaxy ends and where the other one begins? And so this is what the recent study that you can find in the description below decided to do by both doing a lot of simulations using 3 different simulation systems and also trying to establish a kind of an official edge of where the galaxy should technically end. And it's very, very surprising because it's a lot farther than we initially thought. And one of the main reasons is because this, the sort of prototypical galaxy that we're all used to, is actually only a very, very small piece of what a true galaxy is. Today we know that apart from the actual galactic center and the disk itself, there are a lot of other structures inside the galaxy that are technically also part of it. There's obviously things like globular clusters that are connected to the galaxy. There's also a lot of gas around the galaxy itself, but most importantly, the vast majority of the mass is actually in the so-called halo. Now today, most scientists believe that this is consistent of dark matter, but there hasn't really been official proof of the existence of dark matter just yet. At the same time, apart from dark matter, halo also consists of a lot of individual stars, a lot of globular clusters, and a huge amount of dust. As a matter of fact, if I were to try to simulate what all of this looks like without trying to crash my computer, if this is a typical galaxy here, here's what all of this might look like if we were to kind of zoom out of here. This huge spherical object you see around the galaxy is essentially gas, stars, globular clusters, and dark matter. And the amount of gas and stars here is very likely at least similar to the total mass of the actual prototypical galaxy that you see right here. In other words, if you were to take all of this and turn it into a bunch of individual stars and gas, you also get a very similar amount of mass in the halo as well. And this is of course not including the mysterious dark matter. But one thing that this study confirmed is that it's very likely that none of this looks like a sphere. So this halo of gas, stars, globular clusters, and of course mysterious dark matter is very likely very differently shaped for every individual galaxy, depending on various galactic interactions that happen in that particular local group. So for example, for the Milky Way galaxy that's right here and the Andromeda galaxy that's right here, because there's a lot of gravitational interaction between the two, and also because the actual dwarf galaxies that you see right here also interact with the halo, they do sort of turn this into a somewhat different shape, and it's very difficult for us to predict right now what the halo of Milky Way currently looks like. I guess for now this is the best I can do because we just don't really know what the real shape is. Now at the same time, because the distance here is roughly around 1 million light years, it's practically equivalent to half the distance of Milky Way to the Andromeda, and assuming that the Andromeda galaxy also has a similar halo, they're probably already touching and interacting. And this also confirms another study that very recently discovered actual newborn stars being formed pretty much in the middle between the Milky Way and the Andromeda galaxy, which very likely resulted from the collision between two halos. So in other words, what all of this suggests is that not only is our galaxy much bigger and its edge much farther than we initially thought, but at the same time this also tells us that both galaxies are already colliding and creating a lot of new stars and a lot of new globular clusters. So even though we thought that this is maybe what the galactic collision would look like, it's already started, it's already going on, and a lot of new things will be generated in the next few billion years before these two galaxies finally finish combining and turning into a single galaxy, most likely called Andromeda. But I think what always surprised me is how much gas there is in this halo. Like I said previously, the total mass of gas here is essentially similar to the whole mass of the galaxy that we typically see. And although it's kind of difficult to understand or explain at first, but in reality it really makes a lot of sense, mostly because of how galaxies are born, how they grow, and how they interact with other galaxies and gas around them. So today we actually know that once in a while a typical galaxy will become what's known as an AGN or active galactic nuclei galaxy, or essentially what we sometimes refer to as quasars if you look at them from far away. These AGNs are normally defined by an extremely active supermassive black hole in the center that absorbs a huge amount of mass from all of the gas that flows into it, while at the same time creating these very powerful astrophysical jets. And these astrophysical jets, this is the picture from the M87 black hole astrophysical jet, kind of act like typical fountains. They throw out all of this matter really far away from the galaxy and sort of recirculate it back into the halo. But then once in a while, all of this halo gas accumulates into a big chunk and falls back into the center of the galaxy. So it's sort of like a self-feeding fountain of gas and energy. So once in a while the gas gets expelled, then it comes back and starts feeding the black hole again. And we've even observed this as what's known as Fermi bubbles right here in our own galaxy from the last such eruption. This was approximately a few million years ago, and this gas is slowly moving out into the halo, and at some point some other gas cloud might come back and restart the AGN inside the Milky Way galaxy as well. But because these eruptions are always very different, this is why the halo itself is not spherical. It always has these blobs everywhere, and including of course the interaction with other galaxies, it grows into different directions and creates this interesting, unusual shape that's always different for every single galaxy. But for our galaxy, using these simulations, the scientists established that the edge is probably around 1,000,000 light years away, or roughly around 300 kiloparsec or so. But this value might also change as we discover a new dwarf galaxy in the vicinity, and as we understand how all of this sort of influences the size of our own galaxy. And one of the main reasons it's important to kind of understand what the total size of the galaxy is in regards to calculating various galactic interactions. Here, normally, we don't really count the mass and the size of the galaxy when we try to, for example, calculate a velocity of an escaping star or an interaction with another dwarf galaxy. But by knowing exactly how large and how massive the whole galaxy is, we'll be able to get much more accurate results in the future. And most importantly, this will help us one day understand and explain how the Milky Way galaxy was formed and how, essentially, we came to be as well. Because all of this is sort of connected. And just to give you another visual representation of this, here in Space Engine, you can actually even see some of these halo stars and halo globular clusters. They're basically these random stars here and there, like there's one right there, that appear away from the galaxy, but within the bounds of the so-called galactic halo. And they do extend quite a lot, up to several 100,000 light years. And what's interesting is that some of these stars are actually really new. They're baby stars. So the only way that they could have been created is if there was a lot of gas circulating around the halo, and once in a while it would actually initiate the star formation. And as you can see in this particular case, this star even has its own planets. So maybe one day we'll discover a very unusual planet somewhere outside of the galaxy, looking at us and being able to actually see what the shape of the galaxy is. So it's very possible that one day we'll discover such a star with planets orbiting around it, but being completely outside of the actual plane of the galaxy. A few years ago, one of the more popular videos on the channel was actually about UI Scuti. Many people wanted to kind of see how this star, this tremendously large star, compares to basically the rest of the solar system, for example, and some of the other stars and planets in the universe. And this tremendously bright supergiant is obviously not alone out there in the universe, because there are quite a lot of other really large stars we've discovered in the past few decades. Now the thing is, today UI Scuti is no longer on the list of largest stars, and I wanted to talk about two things. First of all, why is it that it lost its status? And second of all, what is the new record holder which by the way is not probably going to last either. Let's discuss the first idea. So these large supergiants in general do not really look like a lot of simulations and illustrations portray them to be. They're not just these spherical balls of matter and energy. They're not just these plasma balls that are almost perfectly spherical. Even our beautiful sun is not, as it basically shifts around and changes its shape just slightly due to various activities. But the larger and the more active star is, the more likely it's going to change its shape even more. So here, as we go with larger and larger supergiants, like for example if I were to place Antares here, it would suddenly cover a lot more space. But its shape becomes a lot more unpredictable. So it's not really a sphere anymore, it's not really this huge plasma ball, it's more of a plasma cloud-like formation that also changes its shape quite dramatically, quite frequently. And so these two former giant record holders, UI Scuti and Canis Majoris, are not really circles, they're not spheres. They're really more like the ever-changing spherical cloud-like formations that do grow and shrink in size quite a lot. This here is actually the Homunculus Nebula, and I thought it was a pretty good example of what it might look like if we were to really come close to some of these stars. This one has two bulges, but most stars will obviously have one. So these stars do frequently change their shapes and sizes. But in this particular case, this is not really what happened to UI Scuti at all. What happened was actually a measurement error from the previous technique we've used. So in other words, when we remeasured its actual size, turns out that it was actually much smaller than we originally thought. So when the original papers came out measuring the sizes of some of the largest stars in the universe, or technically our galaxy because these are the stars we can easily measure, the scientists used the very well-known technique known as interferometry. In general, it's a technique that's been developed over 100 years ago actually, and we've perfected it since then quite dramatically. The so-called radio interferometry, for example, has actually been used to take this wonderful picture of M87 black hole. And the way that it works in a nutshell is relatively simple. Instead of having one extremely large telescope to try to measure the size of something really far away, instead you make a bunch of smaller telescopes and point all of them in the same direction, looking at exactly the same spot at exactly the same time. And the only thing that is different in this case is actually the very minute changes in the arrival time of the light coming from this object into every one of these telescopes. This one is one of the more famous ones. This is the radio telescope known as ALMA, located in Chile. And the most difficult part of this technique is actually trying to calculate the minute changes in the arrival time of light from different objects. So for example, the more telescopes you have here, the more different pairs of telescopes you have to try to calculate this for. And in general, we need some really powerful computers to try to calculate a lot of different data for various stars we've measured so far. This is how we've discovered the size of this object, UI Scuti, and also some of the other stars as well. But unfortunately, this technique was not perfect, because what we didn't really consider is that we measured the distance to this object incorrectly. We overestimated how far away it was. The original measurement of distance for UI Scuti determined that this object was about 1700 times the radius of the Sun, so basically the Sun in comparison here would be really small, but also that the distance to this object was about 9,500 light years away from planet Earth. But turns out that the distance was much closer. The distance to UI Scuti now stands at about 5,100 light years, or basically almost twice as close as we used to think it was. And the reason for this new measurement, which is actually really accurate, is the beautiful Gaia telescope. In the last few years, the ESA's Gaia telescope has done a really good job at measuring the extremely precise motions of all of the stars in the relative vicinity, with the actual measurement of about 1 billion nearby stars and their exact position, exact motion across the night skies, and obviously distance to those stars as well. So now we have this data for all of these really bright stars, and one of those stars turned out to be UI Scuti. We didn't really know it right away, but some of the recent recalculations of various stars that we used to think were farther or closer to us have now established that our measurements originally were not really correct. This was UI Scuti's case, and because it's much closer to us, it means that it's not really as bright or as large as we thought it was. And its size shrunk to being this to now being somewhat similar to this. Basically, it's now not even in the top 10 largest stars, it's like somewhere in top 100 I think. which is of course something that many scientists expected because this happened many times in the past and will definitely happen in the future as we improve our measurement techniques. With UI Scuti, the original error was not really that large, but the distance was never really questioned until relatively recently. And even though the interferometry technique generally is really accurate, it's not as good at determining distances as it is at determining the actual size of an object you're looking at. And all of this new data coming from the Gaia telescope is most likely going to revise a lot of other star measurements as well, mostly because in astronomy or really any other science, things change all the time. You can never really assume that something is going to stay either the largest star or the most massive star or the most whatever for a very long time. We always find something new that's bigger, better, and more extreme. But now that UI Scuti lost its status, what is the new largest star ever? Well, it turns out that it's the object known as Stephenson 218, although it's also possibly the object known as WOH G64. Although I really wanted to say this with a Klingon WOH G64. Sounds a lot better. But anyway, so these two stars are now the contenders for the biggest star ever, with Stephenson 218, or 2-18 I guess, being part of this relatively small cluster of stars known as Stephenson 2. And it's basically the 18th star in there. What makes Stephenson 2 cluster interesting is that it seems to possess quite a lot of these really large supergiant stars, many of them only about 10 to maybe 12 million years old, and many of them will eventually go supernova and create even more unusual but much smaller stars in the future. So it's a pretty interesting cluster. It was very likely created from a relatively large molecular cloud that eventually caused all of these stars to form around the same time. And now they're all going through their later stages where they turn into these gigantic objects known as supergiants. And it seems that this particular cluster seems to possess a lot more of them than any other cluster we've seen so far. So this is definitely a pretty interesting destination and will result in a lot of different Type 2 supernova in the coming years. Although not anytime soon, we're talking about thousands or possibly even millions of years. The current estimates for its size put it at even larger than the original estimates for UI Scuti, so making it about this big. But once again, remember, this is not a true sphere. These are more like molecular clouds that do shrink and change in size. Also, for this particular star, the actual size uncertainty is really large. Some estimates put it at only about this big. So there's definitely going to be a lot more discussion about how truly big this star is, and so there's a big chance right now that it might actually lose its status relatively quickly as well. And in terms of distance, we think it's about 20,000 light years away from us, like all of the other stars in this cluster. So in that sense, we think that the measurement for the distance is somewhat correct, although it might still change as well, just like it did with UI Scuti. And since there are like 26 different red supergiants in this particular cluster, it's also very likely that at some point, because these objects do change their size quite a lot and with time they do grow a little bit bigger, some of them might even take over and become even larger than the object that we currently refer to as Stephenson 218. And for the most part, all of these stars are basically just in part of their evolution where they're transforming into larger and more active stars. At some point, they're all going to become what's known as a Wolf-Rayet star that starts throwing out a huge amount of matter and eventually goes supernova. So this is basically just an evolutionary part of their lives. Our Sun is actually going to go through something similar, but because it's a lot less massive, it's going to have other evolutionary steps. And right now, it's actually in a stage where it's fusing helium, but still has a little bit of hydrogen left. So it does have a few million years to go before it actually reaches the stage of basically supernova. Although unfortunately, there haven't really been that many studies about this star, and it's very likely that because it has the status of #1 biggest star ever now, and by the way, this is the only image I could even find of this star, this probably is going to become a much more popular topic for future studies, and we're probably going to learn a lot more about it. Right now though, we don't really know enough. Although judging by its age and also its activity, it probably does not really have any planets, or at least planets that are stable. It might have some planets being formed, but they're not going to last very long because this star is definitely going to go supernova before they finish forming. So I highly doubt we're going to find anything similar to this, or better even this. A world that might possess some sort of liquid water on the surface. This is actually what one of the planets in Space Engine looks like for UI Scuti, and even though these stars do have habitable zones, they're unlikely to have these conditions because of their age. They're not old enough to have these fully developed planets with liquid water on the surface. But anyway, we'll definitely come back and talk more about some of the more unusual stars, specifically the largest stars out there, in some of the future videos, but for now I guess that's it. So, turns out UY Scuti is not the largest star anymore, although that was expected. When Canis Majoris lost its status, many people kind of were sad as well, but now we're going to have another contender for at least a few years. Once we discover another object, we'll definitely talk about this as well. Until then, thank you for watching, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something you may have not known before. Also, thank you so much, the person by the name R, for bringing this to my attention, because I actually totally missed this as well. This was one of the comments in one of the videos, and I had no idea that UY Scuti lost its status as well. Thank you for bringing this up, and, well, I guess, if you have anything else to add, let me know in the comments below. Our own solar system seems to be actually a little bit closer to the central region of the galaxy, including the central black hole. And our sun also seems to be moving faster around the galaxy than we initially thought. In other words, it looks like Earth is much closer to Sagittarius A-star black hole after all. Now, only a little bit closer in terms of the previous numbers, but when I say a little bit closer, I mean like 1,000 light years closer, which is actually quite far. But let's talk a little bit more about this analysis and also about the details of this study. And here I think it's really important to understand that it's kind of difficult for us to study our own galaxy from within it, especially when it comes to calculating distances and calculating sizes of different things. And the main reason for this is because we're looking at everything from essentially one of the galactic arms of the Milky Way. And in some sense, it's sort of almost like trying to create a map of your own house by being somewhere in for example, a shower with the curtains closed. It's almost impossible, or at least extremely difficult, to actually see everything in the galaxy by being where we are. But it doesn't mean that we can't try, and as a matter of fact, we've been doing a pretty good job at figuring out where things are and figuring out all of the other things about our own galaxy, including the shape, the size, and what's inside of it. But the original calculation of where the Sun and the Earth were located compared to the center of the galaxy were originally done back in 1985 and were estimated to be just a little bit over 27,000 light years, which would place it somewhere around here, with the average speed of the Sun moving around the galaxy being about 220 kilometers per second. And this wasn't really questioned much until the study from last year estimated the distance to be closer to about 26,500 light years, and this also meant that the Sun was moving a little bit faster around the galaxy. But these calculations were still not perfect and did rely on some of the data that has since been changed. And what's really important to also understand is that, thanks to a lot of different new projects, including the one right here from Japan, known as VERA, which is a very exciting radio astronomy project that's using a very interesting technique known as very long baseline interferometry. And the best example of this technique was when these telescopes you see on the screen were able to combine their data, creating essentially a telescope size of planet Earth, and using this technique, after several years of observations, the scientists were able to create this beautiful picture, the first ever picture of a black hole. But the Japanese VERA is obviously much smaller. It's really just using the telescope roughly the size of Japan as you see in this picture, but because it's all in Japan and because essentially they're using relatively similar techniques, it's much easier for them to analyze data, and it's a lot quicker to actually analyze everything around us. And so not so long ago they released some of their first initial results, and the results were extremely interesting. In this case, they weren't actually looking at black holes, they weren't really looking at any unusual things, they were just looking at various radio signal emitters around the galaxy, and they were trying to calculate their precise motion and precise location in the galaxy. This is what we usually refer to as astrometry. And in this case, they were looking at these objects known as masers, which essentially is kind of like a laser that emits microwave light instead of optical light. There are lots of masers around the galaxy, and usually they're produced by different types of objects, but in most cases we know what produces them. And so they looked at about 99 of these masers for a period of 1 year, because it also allowed them to use the motion of Earth around the Sun to then calculate the amount of parallax and thus calculate the exact distance to these objects. But because they were using a telescope dish that was roughly around 2600 kilometers in diameter, They were able to calculate all of this to extreme precision, which also allowed them to calculate not just the distance but also the speed of these objects, and of course establish where they were located compared to everything else in a galaxy. And following the initial processing of this early data, they were then able to create a relatively accurate estimate of where everything is located, but most importantly, where our sun is located compared to everything as well. And obviously the results are different from what we initially thought. We are much closer, about 25,800 light years away from the center of the galaxy, and also it seems that Earth is moving around the galaxy with a speed of about 227 kilometers per second, which is about 7 kilometers per second faster than the previous assumption. Now obviously this might not sound like a lot, and also it might not seem like a big change, but when it comes to precision and measurements in space, and especially in our own galaxy, this is actually a big deal. It also means that maybe certain things we assumed before will need to be recalculated as well. And just to give you an example here, the difference in distance here is basically as if we suddenly found ourselves in the middle of the Orion Nebula, which is around 1300 light years away from us. So basically that's by how much the distance changed. But this value might change again in the future, because now the Japanese scientists want to include other Asian telescopes into their observations as well, essentially creating a kind of a East Asian network which will allow them to calculate things even more precisely. Although chances are the values are not really going to change that dramatically anymore. This was a pretty accurate observation, and it does seem to have just enough data points and enough analysis to suggest that this is a pretty accurate value both in speed and in distance. However, this might change some of the previous analysis, for example, of different energy events coming from the center of the galaxy, which did rely on this outdated distance value. Since the value changed by roughly around 7 to 8%, it does mean that some of the previous calculations may have been slightly exaggerated. But it's also really important to do these observations and these calculations because it allows us to sometimes solve certain mysteries. One good example of one recent mystery and recent anomaly that was actually due to a distance miscalculation was a discovery of a black hole with unusual mass that didn't make sense. Turns out when the scientists recalculated everything, the star where the black hole was most likely located was actually much closer to us, and thus the black hole had much smaller mass. And this suddenly explained everything very well. The black hole was not anomalous, nothing was unusual, and everything was just as it should be. But as always, trying to calculate distances in space and also trying to see how far away things are and even how fast they're moving is usually very difficult for us. Because here we're essentially trying to create a three-dimensional image of everything by just seeing things in 2 dimensions. Because from our own perspective, from planet Earth, everything just kind of looks like a big map. Nothing here is 3-dimensional. And that's why surveys like the one that Japan just completed, and about which you can learn in the description below, allow us to slowly get closer and closer to a perfect recreation of the Milky Way galaxy in 3 dimensions. Now I think most of you are probably familiar with so-called SETI, the Search for Extraterrestrial Intelligence Institute. It's been around for quite a while and it has a lot of different programs going, but its main purpose is to try to discover extraterrestrial intelligence somewhere out there in space. And SETI is not just trying to find alien life. This organization is really trying to find intelligence somewhere out there in space, and it's used a lot of different techniques to try to discover if someone out there is trying to communicate with us, or if anyone is trying to listen to our communication as well. Now, in one of the videos I made last year, I mentioned one of the previous studies that discovered that, well, it seems that no one is trying to talk to us. It seems that no communication is coming from anywhere. In other words, the study suggested that there might be no extraterrestrial intelligence, at least from all of the data we've collected so far. But there is a bit of hope in trying to discover what's going on, and this hope is coming from the study that was just recently published that you can also find in the description below. This study is based on observations of various stars and trying to identify any changes in those stars in the last few decades. Now, more specifically, this study actually began back in 2016 when the scientists from Sweden discovered that when trying to compare the images of the night skies that were taken back in 1950s with the images that were taken today, there was at least one star kind of missing, as if it just disappeared. The original data from the 1950s came from one of the biggest observatories back then, the United States Naval Observatory. This beautiful observatory was actually in the forefront of trying to look at the night skies, and back then it was actually used for mostly navigation reasons, but it also had a scientific component as well. So this was one of the top observatories, but because it was built in the urban area, eventually it became very difficult for scientists to use this place because there was just too much light pollution, and other observatories were much better at looking at the night skies. Nevertheless, even today it's known for its huge collection of atomic clocks, and also the biggest astronomy library in the United States, and one of the biggest collection of astronomy related studies in the entire world. So it's a very important place. And back in 1950s, and also basically until very recently, the observatory was creating these night catalogs of the entire night skies, and they were very detailed and were also used in a lot of different studies, as well as of course for naval use by the United States Navy. But when the scientists behind the 2016 paper compared the 1950 observation with some of the more recent ones, they realized there was at least one star sort of missing from the picture, as if it just vanished. Now this wasn't really a big deal back then, but now they published a follow-up observation of other stars they've discovered. In this new follow-up, they discovered approximately 100 different stars that disappeared over the last few decades. Now, what do we mean by disappeared? Well, imagine looking at the night skies and basically recording all of the data and collecting all of the star information, and suddenly, when you look at it a few years later, one of the stars just disappears. It's no longer there. With no explosions, no appearance of any kind of black hole formation or neutron star formation, and no other signs. But what does this have to do with aliens? Well, it might have nothing to do with aliens, or it might imply that something is going on in this region of space. More specifically, of course, it could be the signs of a very advanced civilization creating what's known as Dyson spheres. These huge formations around a star to try to harness as much energy as possible. Now this is the most eccentric explanation to what's happening, and this is actually probably the least likely right now. But because these scientists were able to discover 100 disappearing stars, it creates a mystery that definitely needs to be investigated. Simply because it's either a phenomenon we've never observed before and we can't really explain right now, or it could imply that in that particular region of space there might be a very advanced civilization building these huge shells around stars that eventually turn these stars into these very efficient energy batteries that produce a lot of energy for this civilization but make them invisible to everyone else in the galaxy. And even though humanity currently theoretically understands how one would form something similar to the so-called Dyson sphere that covers the entire star and produces energy by capturing it directly from the sun, we are far from being able to create this ourselves, and the difficulties and engineering challenges involved here are just beyond what humanity is capable of right now. This, however, is one of the explanations for how these stars might have vanished. The other explanation is actually a lot more likely, but a lot less exciting. So if these stars were, for example, what's known as flare stars, it's very possible that when the original pictures were taken, the star actually experienced a tremendously powerful flare that made it extremely bright, like much brighter than even what you see here. And then when we took a picture the second time, it was just much quieter and practically invisible to a typical telescope. We would need to use a much more powerful telescope to see if the star is still here. So these M-type superflares are actually one of the more likely explanations, but there needs to be a lot of follow-up to discover what's going on. On the other hand, these events could also be similar to what's known as red luminous nova, or basically a very unusual supernova that are not really typical and are not easily explained. In other words, once again, this was a sudden brightening of the object for one reason or another that was not initially explained or even detected, and now the star is just a lot more difficult to see because it's naturally dim compared to what it was when the original picture was taken. Just to give you a visual analogy of what might have happened here, You have a bunch of stars. Some of these stars might have suddenly become really bright. This is when we took the original picture, and then when the follow-up pictures were taken decades later, none of this was visible anymore. Essentially, these were some temporary events that very likely brightened the star in some dramatic way, possibly an unusual type of a supernova or nova, and now these stars are just not very visible. Once again, to try to discover if this is what happened, we have to use more additional observations using more powerful telescopes to try to see what really happened in those specific spots that were identified by this team. And obviously there could be other natural explanations for what we're observing and how these stars are disappearing and are no longer visible to us, but leaving this as a natural explanation is not really what SETI is about. I'm very certain that some of the follow-up studies from SETI would definitely address this and try to resolve exactly what's happening to these stars and why they're no longer there, or at least appear not to be there. Which is of course why I'm going to follow this up with another video sometime in the future. For now, that's really unfortunately all we know. We know that some stars seem to have disappeared, and some scientists think that maybe it's aliens. Because, you know, maybe they built a huge Dyson sphere and the stars are just no longer visible. But that's just a speculation. We'll find out in the near future. So what you're looking at right here is a simulation of the previous record holder, the so-called fastest star in the galaxy. This is the star known as S2, and right around here at the closest approach of its orbit, it's able to reach the velocity of about 2.5% of the speed of light, or around 7,500 km per second. And the scientists have quite extensively studied these so-called S objects, which are essentially stars, very compact stars, really close to the center of the galaxy. But very recently, the German scientists, whose paper you can find right here and also in the description below, discovered another star, another record holder for the fastest star in the galaxy, even faster than S2. The star, now known as S62, seems to have a very unusual orbit, very eccentric orbit as we usually say, which as you can see right here seems to be very different from any other object in this region. S62 takes approximately 9.9 years to go around Sagittarius A star, the central black hole, once, and as of today this is one of the more unusual stars we've discovered so far. Although this does not include the so-called G objects about which I've talked in the previous video from a few months ago. G objects are still the weirdest objects in this region, and you can learn more about these objects in one of the videos that's going to be popping up around the end of the video. But why is this called the fastest star? Well, it's because, once again, at the closest approach to the black hole, which is what we refer to as periapsis usually, the star itself moves at around 10% of the speed of light. That's about 30,000 km per second. Just to give you a perspective here, the fastest man-made object, which is of course the Parker Solar Probe, is going to reach its highest velocity in 2024 when it's at the closest to the Sun. And so right here at the periapsis of its orbit, at the closest approach to the Sun, the maximum reached velocity is going to be, let's see in a few seconds here, so it says here approximately 190 km per second. That's dramatically lower than the 30,000 km per second that S62 has when it approaches Sagittarius A star, which is also about 4 times higher than the previous record holder S2. Now, why does it have such a high velocity? Well, it's of course because of the unusual elliptical orbit. When it comes to orbits, if I were to give Parker Solar Probe a more circular orbit, in other words, if I were to decrease its eccentricity from about 88% to, let's just say, 0, the velocity would now drop to about 139 km per second. And so essentially, the orbital parameters always depend on the shape and the proximity to the object that is being orbited. So in this case, the eccentricity of the orbit of S62 is responsible for giving it such a tremendously high velocity. And I tried to kind of recreate this in Universe Sandbox by using a model of Sagittarius A star and just a star similar to our Sun right here. And you'll notice that right around this area, the velocity is actually close to about 30,000 km per second as well. And the closest approach here is equivalent to the distance of the Sun to, I guess, a little bit closer than Uranus. So in other words, maybe about 15 astronomical units or so. And this kind of a behavior and this kind of an orbit is very difficult to explain. So somehow this unusual star that's about 2.2 masses of the Sun was able to survive for a relatively long time in this region, and it doesn't seem to have any signs of being disrupted or being stretched or anything. It approaches the black hole really closely and then leaves really far for the next 9 years. The farthest distance here is probably around 1,000 astronomical units or so, and so most of the time the star spans away from the black hole and then for probably only a few months or even just a few weeks approaches this region right here and ends up moving really fast in this region. But we really can't explain how this star got this orbit. One of the main explanations right now is that it possibly had a partner, basically another star in orbit, and this partner somehow got kicked out of the system or possibly even swallowed by the black hole, and this of course left the main star with a very peculiar orbit. And because these two stars act on each other as they orbit around one another, if you were to remove one of the stars, the orbit of the other would change as well. And this is how we think maybe it acquired this unusual eccentric orbit. But to have this really extreme orbit, a lot of things need to happen, and the fact that this star did not fall into the black hole is a mystery. At the same time, in one of the previous videos, we've talked about how some stars can naturally form around black holes. It's quite possible that this is one of those stars that was formed in this orbit from all sorts of material that was left around the black hole in its accretion disk and also in its neighborhood. And this of course could have resulted in the production of several of these S objects. We currently refer to this region as the so-called S cluster, and for the most part we don't really know how these stars were created. The most prominent theory is that they were captured from other regions, but we don't really know, and they could have been just naturally created around the black hole. But hopefully by studying S62 in a little bit more detail, and by identifying specific features of this star that other stars might not have, we'll be able to answer the question of its origin. Now right now we don't actually even know what's going to happen to the star, but the chances for it to collide with something and probably even fall into the black hole are pretty high. What is, however, pretty interesting about S62 is that it appears to be very similar to other stars in this region. In other words, if we were to look at all of these S objects orbiting around the black hole, they all seem to possess very similar features. They do seem to be compact, they seem to have relatively similar brightness, and they do appear to be star-like, not like the G objects I've discussed previously. And so in some sense they probably do have similar origin, and discovering this will probably be quite a mystery to resolve. Now, one thing we need to understand is that even though the simulation makes this appear as regular space, nothing here in this region is regular. This is an extremely dense region. Here there's a lot of material, a lot of different energy, and the black hole itself creates very inhospitable conditions. Here the density is much higher, like thousands of times higher than the density of space where we are, and there's millions and millions times more energy and more very energetic events happening here on a regular basis. So it will be very difficult to imagine what's really going on here unless we do more thorough observations and try to simulate them here using supercomputers. But one thing we need to remember is that this region is extremely different from the space where we are. The actual density here is much higher, so there's like thousands if not millions of more particles in the actual space, and at some point some scientists even suggested that the region around the black hole is almost like some kind of an atmosphere. There's a lot of particles here that do interact. While at the same time this is also an extremely active and extremely energetic region. There's like millions and millions times more energy here, there's a lot of radiation, a lot of various stuff going on, and this is an extremely active environment. So in some sense, trying to imagine this from our perspective here, where the solar system is going to be really challenging. The only way we can probably imagine what's happening here is by simulating it using supercomputers, because it's very difficult to see that far. Now, one day we might be able to answer the question to all of the mysteries around the supermassive black hole, and one day we might be able to understand what's happening here. But discovering stars like S62 is a very important process of us getting to these answers. Now, why do we want to know these answers though? Well, one of the reasons is because, as I discussed in previous videos, we know that our black hole did erupt a few times, and some of these eruptions were really powerful. So if one day S62 decides to collide with our black hole, a huge amount of radiation is going to be released, and we need to understand if this is something we need to be worried about. If the so-called Fermi bubbles that we discovered a few years ago were actually formed by a star collision with a black hole, we kind of need to understand if this can happen again, and if this is something humans might potentially not survive. So these studies are pretty important, and understanding what happens in space and how it affects us is also extremely important as well. we are indeed flying through a supernova that most likely occurred several million years ago. So let's talk a little bit more about what all of this means, and most importantly, how we know all of this. Now, first of all, if you were to look from the inside of a supernova cloud, you wouldn't really be able to tell that you were inside of one. It's very challenging to see all of this simply because you would have to leave the supernova and look from the outside to realize where all of the stars are located. But there are very clever techniques and very clever ways we can discover where the sun actually is located. So first of all, we know that our solar system is flying through the region known as a local cloud. This is a pretty large region, several light years across, but we don't know what created this, and we also don't really understand what and how it was created. But what we do know is that it represents a slightly higher density compared to normal vacuum, and also the actual particles inside of this cloud, which sometimes is also known as the local bubble, is about 7,000 degrees Kelvin. But these very hot particles would not really cause any damage to, for example, spacecraft flying through this, simply because of an extremely low density. But it was always believed, although never proven, that this local cloud was indeed created by some sort of an ancient supernova. The modern calculations suggest that the solar system entered this region maybe about 44 to 150,000 years ago, and is going to continue moving through this region for another 10 to maybe 20,000 years. But in order for us to understand what this could have been made from, and also whether we are flying through a supernova, what we have to study are the deposits of various types of isotopes on our own planet. And one of the easiest isotopes to connect to supernova is an isotope of iron known as iron-60. Unlike more stable isotopes of iron, iron-60 has a half-life that's roughly around 2.6 million years, meaning that if we find it somewhere on the planet, it couldn't have been here from a very long time ago. It was only probably created within the last few million years. And the best known source for iron-60 is, of course, all sorts of beautiful supernova we've observed in the last few years. And in the last few years, many different studies were able to find iron-60 in various locations and also various types of deposits on the planet. For example, this older study by the same scientist discovered the iron deposits that was roughly around 2.6 to 6 million years old, suggesting a slightly older supernova that most likely bombarded the planet, depositing all of this iron on the surface and eventually turning it into sediment. Another study from Berlin Institute of Technology produced this beautiful 3D map of the probable location of iron-60 around the local bubble that we're being bombarded with right now, which not so long ago NASA was even able to discover in space around the planet. This was actually done by the Advanced Composition Explorer that's still active and working in space right now. And the most recent paper was able to discover iron-60 inside of 33,000-year-old deposits that were collected from deep sea sediments, which of course also suggests that the planet even back then was already bombarded by iron-60. And all of these recent papers indicate that for the past 33,000 years at least, we've been traveling through this unusual region where a very large and a very powerful supernova occurred. The supernova that most likely also influenced the conditions on our planet, at least to some extent. Now we know that the supernova here occurred within the last 15 million years because any iron-60 mostly disappears completely within 15 million years. So this large cloud that Earth is traveling through right now is only a few million years old, and possibly even a few thousand years old, and this is actually where the scientists currently are not entirely certain. For example, one of the recent studies from Antarctica discovered that there's also a little bit more of this iron-60 that was deposited here only a few decades ago, and all of the ice core samples from the last 20 to 30 years contain a little bit of iron-60 in them as well. In other words, we know that this is sort of a continuous process that has been going on for at least some time now. But right now what we don't know is whether it's connected to these samples from 33,000 years ago and to these samples from a few million years ago. And although it's quite possible that the local bubble or the local cloud is indeed responsible for these detections, and it's also possibly produced by some sort of an ancient supernova, there's still a chance that there is something else going on that's not related to the local cloud at all. And that's one of the questions these scientists want to try to answer. One of the major ways we can discover the answer to all of this is by looking for even older samples, something older than 40,000 years old. And if we do discover iron-60 in these samples as well, and most importantly if there's even more iron-60 in these older samples, it only suggests that the local bubble is probably not related to this, and that another supernova occurred anywhere from 40,000 to possibly 100,000 years ago, and we're sort of now traveling through that particular region. However, if more recent samples from about now up to about 30,000 years have a lot of iron-60, way more than in the older sample, the only reasonable explanation here is that by moving through the local bubble, we're now experiencing more iron-60, which of course means that the local bubble is indeed a supernova remnant. Which also might lead to some new investigations in regards to how this local bubble affects the conditions on our planet and how it might even affect the climatic changes as well. Right now we obviously have no idea what happens to stars and of course planets as they move through supernova remnants, but this is something that we would love to learn more about, especially if it's actually something that's affecting our planet right now. And chances are in the next 10 years or so we're going to have a final answer to all of this as we discover more samples and as we learn more about the unusual mysterious iron-60 that's bombarding our planet and has been doing so for at least 30,000 years now. So it's most likely definitely related to some kind of a supernova. We're just not entirely sure which one and where all of this iron is coming from. It could actually have other sources as well, but that has to be discovered just so we can understand how all of this affects the planet. The legend has it that if you say his name 3 times, he's going to appear behind you. Betelgeuse, Betelgeuse, Betelgeuse. Oh hey, it worked! Hello wonderful person. On that cheesy note, today we're going to be talking about Betelgeuse once again, and the recent study and recent analysis of what's been happening to it, which might have kind of actually answered a lot of questions. By the way, here's the little tiny sun in comparison to this object, and what the recent study discovered corrects our mistakes of the past. We might have been wrong about a lot of things in regards to Betelgeuse, specifically its actual size and, of course, its distance to our Sun. It seems to be about 25% closer and it seems to be smaller. But more importantly, unfortunately the show has been cancelled. It's very likely not going to go supernova for at least 100,000 years or longer. So let's discuss the study, the findings, and of course a lot of other details about Betelgeuse that we've discovered in the last few months. And let's begin with the name itself, which by the way currently still doesn't really have a very good explanation, but we know that it comes from Arabic and we know that it comes from this ancient book by Abd al-Rahman al-Sufai, an ancient Persian astronomer who wrote this book back in 964, which is basically 1,000 years before that, where he had a very detailed illustration and essentially naming and explanation of various constellations in the night skies. This was during the so-called Islamic Golden Age, which unfortunately came to an abrupt end when the Mongolian tribes invaded and essentially destroyed most of the prominent cities in the region, including Baghdad, that back then was the center of the world, at least economically, culturally, and commercially. But that's of course beyond the scope of this video. The idea here is that, well, back then he drew the picture of this, which was the representation of what we know as the Orion today. Another way of seeing it is of course using the Western astrology, and here this is what the Orion looks like for us. In both the Western and Arabic astronomies, or technically astrologies, the star right here represented the arm or the shoulder of whatever this shape was. Here's actually what Orion looks like in typical Western mythology, and essentially the bright star is his shoulder, or in this case, his hand. And it just so happens that the name written here, and specifically the name of this region right here, is Yad al-Jausa. Al-Jausa is the Arabic name for the Orion constellation, and Yad represents hand. Eventually, with time, it sort of changed into Bait al-Jausa, and because the Europeans read it differently, it became Betelgeuse. So this is essentially where, unofficially at least, the name comes from. Officially, we're still not entirely certain how all of this transformed, but we know that this is where it starts. And as you probably already know, and may have seen from other videos, the star has been giving us a lot of new mysteries to deal with in the last year or so. So this, on the left here, is what it looked like a year ago. Then on the right you see what it looked like in around January of 2020. And this major change in brightness is what suddenly made this star extremely popular on the web, and also created a speculation that maybe it's about to go supernova. Well, the answer to the supernova question is an almost definitive no, but the answer to the dimming and why it decreased in brightness so much still doesn't really have a very good explanation, but the new paper may have actually just explained at least some of the mysteries. So first of all, we know that Betelgeuse is an old star, it's an expanded star, and it's also a very large object. Once again, here's how it sort of compares to our own sun, at least from our previous understanding. Now, if we look at the visual observations of Betelgeuse from 2018-2019, and then we start looking at what happened now, we'll see that there was this sudden dip right here, and also another sudden dip right here. This one obviously was not as big, but this one was really big. Both of them, however, are problematic. The first dip didn't make sense because it was just too much. We've never seen anything like this before. The second dip didn't make sense simply because it didn't happen at the right time. It wasn't really matching with what we originally anticipated. And at the same time, neither one of them had a really good explanation, or at least an explanation that would be accepted by everyone. Right now, the biggest dip is explained as either some sort of a dust cloud that passed in front of a star and blocked the very large part of the star, or another explanation, actually a much more likely explanation, would be essentially this: a very large sunspot or star spot in this case, Betelgeuse spot. This star spot would be big enough to essentially dim the star, and would be probably big enough to do this again probably sometime next year as well. And one of the reasons why some scientists believe it was a star spot is simply because of the observations in different frequencies coming from the star. They noticed that if this was dust, we would actually be seeing different dips in different frequencies because certain frequencies go through the dust much easier. But because all of the optical emissions were more or less the same, it only suggested that the entire star dimmed for some reason, and the best explanation in this case would be a very large spot. But once again, there's really no good explanation for what happened here just yet. But the second dip that happened not so long ago does have a pretty good explanation now. The explanation presented in the paper you can find in the description below. It looks like the second event was actually caused by a very natural and very predictable pulsation of the star that is somewhat similar to, well, in some sense, an earthquake, or technically a starquake. But the reason this is interesting and the reason this is so important is because it relates to a very important study that actually started not so long ago, known as astro-seismology, or astro-seismology, depending on where you're from. Anyway, so the idea here is that stars, like planets, get earthquakes, starquakes. These quakes create waves on the inside, and they actually cause stars and planets to sort of change and to create various effects on the surface. Now, we've learned a lot about earthquakes from planet Earth. We've also learned a lot about the sun from sunquakes, which actually stemmed from the idea of earthquakes. So by seeing what's happening here on Earth, we were able to analyze the sun, and now by studying the sun, we can actually analyze other stars as well. Now, the video I made previously that should be popping up somewhere right there about astro-seismology explains this field in a little bit more detail, but it's essentially an extremely important field in helping us understand how stars evolve, how stars act on the inside, but most importantly, it actually allows us to analyze the star and its composition, its age, and of course its shape by studying these pulsations from starquakes and then by comparing them to what we know about our own sun. And according to the study, what we've witnessed right here is just one such pulsation. Essentially, it was something related to a kind of a starquake happening inside Betelgeuse, and the pulsation itself was caused by a tremendously large pulse wave, or essentially kind of like a sound wave that traveled across Betelgeuse, changing its brightness just enough for us to witness. So in some sense, what we've witnessed is basically a really large earthquake, starquake, Betelgeuse quake happening approximately 530 light years away from us. Which, by the way, is an excellent segue into what we've discovered by studying this emission. Turns out that Betelgeuse is much closer than we originally anticipated, about 25% closer as a matter of fact. And the reason we think so is because of this analysis here. By studying the pulsations coming from Betelgeuse and by analyzing the quake itself, And also by combining all of this with decades of observation of Betelgeuse, the scientists in this paper were able to figure out the frequency of this pulsation, allowing them to see how frequent these pulsations could be, and comparing them to the theoretical astro-seismology models from other stars and from other observations, which also allowed them to recalculate how massive the star is, and also recalculate its total age and its total size. And the size recalculations suggested that Betelgeuse is much smaller than we initially thought. And although visually they still kind of look similar, you can see that the Betelgeuse on the left is somewhat smaller than the Betelgeuse on the right. In terms of the actual numbers, the previous value for Betelgeuse was around 887 radii of the Sun, which is around 617 million kilometers, but the new value is closer to about 764 radii of the Sun, which makes it, I guess, around 14 to 15% smaller. And because it's smaller in size, when we look at its total brightness, we can thus estimate the distance. I mean, technically we can even try this here. So what we're trying to do is essentially take this left Betelgeuse and move it close enough to us that it starts looking about the same in size. But here you'll notice that the other Betelgeuse is farther away, even though from this angle here they look pretty much the same. And what all of this means is that it must be closer to us in reality as well. Even though initially we thought it was about 650 to maybe even 750 light years away from us, it looks like that number is closer to about 540 to maybe 550 light years. Which, by the way, is not the first time that we've ever changed our opinion about its distance. Because when it comes to measuring distances of variable stars with variable properties, especially ones like Betelgeuse that seem to dim very unpredictably, it's somewhat difficult. Because we don't really know what the total brightness here is, there's really no good way for us to measure the distance to this object. But because of astro-seismology and our advances in understanding of how quakes work inside stars, we now have a much better way of determining distances and other properties of these stars. But even at this distance, even though it's closer to us, if hypothetically it did go supernova right now, it would still be far enough from us to do any damage. If this was about 10 times closer to us, we would probably start worrying. But at these distances, the danger is just not there. It would make for a pretty cool show, but it wouldn't really be hazardous to planet Earth. And the other major discovery coming from this astro-seismology study is that it showed that Betelgeuse is basically currently burning helium. And here's one way of trying to understand what's happening there. Right now our Sun is a main sequence star, and essentially it has a hydrogen burning core, and the outer layer here doesn't really burn anything. Eventually our Sun is going to become what's known as a red giant, and this is when the hydrogen in the shell is going to start burning a little bit, but the helium core that's going to start growing larger and larger in size is not going to have any reactions on the inside. Eventually the star transforms and begins burning helium as well, usually in the core, which eventually starts transforming the star and eventually burning other elements as well. But at this stage, when it's still burning helium, it still has at least 100,000 years left in it, and most likely even longer depending on how much material is present there. And the reason the scientists know this is essentially by studying these quakes on the inside and learning how frequently these pulsations happen. So in a nutshell, by studying the astro-seismology of Betelgeuse and by looking at decades of data coming from various telescopes, we might have solved at least one mystery of this beautiful and somewhat unusual star. We might have solved the mystery of the second most recent dimming event, but we still don't really know what happened approximately 9 months ago. We still don't know why it dimmed so much in January of 2020. In the past few years, we've talked a lot about various types of habitable planets and possibility of finding these habitable planets somewhere out there in our own galaxy. But what about super-habitable planets? Planets that are even more habitable than Earth? Well, that's a completely different question, and it's a question that this recent study decided to investigate. Hello wonderful person, this is Anton, and today I wanted to talk about certain discoveries coming from this study that go as far as identifying 24 specific planets out there in the galaxy that could be super habitable, more habitable than planet Earth. So let's discuss this in more detail, but first, I guess a quick reminder that habitability, or the idea of habitable planets, is still a topic we're kind of learning about as we go. So the idea of habitable zone, for example, this green area where Earth is orbiting, is essentially based on the ability for liquid water to exist. But today we also know that liquid water can exist in other conditions, and at the same time, certain planets like Venus and Mars that are also in this area are not habitable. So in this sense, when we talk about habitability or super-habitability, like in this paper, we're really talking about planets somewhere out there that have properties that are even better suited for life than currently we can find here on planet Earth. So for example, a planet like the one you see on the screen that possesses just the right conditions for liquid water, but also possesses better conditions for life to have potentials to evolve for billions of years, and also a planet that orbits just the right type of a star that's not too active and not too cold. And in this case, this study identifies these features very specifically. So for example, when it comes to the type of a star that this planet should be orbiting, they believe that even the star like our own sun is maybe not perfect, simply because it doesn't really have enough life in it. Our sun only has about 5 billion years left in it, but even in the next 2 billion years is going to actually reach conditions where the life on Earth will most likely not be possible anymore, at least the life as we know it. Only extreme life will survive. For this reason, they believe that the best chances we have right now is looking around K-type stars. Our sun is the G-type, it's slightly more massive and it's also a little bit hotter. And on the opposite side we have the M-type or the red dwarf stars, which are normally a lot less massive. They also survive for trillions of years, so even longer than the K-type stars. But unfortunately these are also usually the ones with the most activity. They are what's known as flare stars and can produce a lot of dangerous radiation. So right in between our sun and the M-type are the K-type stars. These can usually survive for up to about 80 billion years, so anywhere from 5 to 8 times longer than the sun, allowing any planet around them to have just enough time to develop life and to have this life evolve for billions and billions of years. And since it took nearly 4 billion years for complex life, including ourselves, to evolve on planet Earth, it means that we need at least 4 billion years, hypothetically of course, somewhere else to possibly have similar effects. And K-type stars right now have the highest chance of allowing for life to thrive here. But there are other factors as well. One of the bigger factors is the moon, which by the way this hypothetical planet has as well. Now having a massive moon for a planet is extremely important in stabilizing various types of wobbles, specifically the changes in the axial tilt that usually our moon stabilizes. Because of this, the planet Earth only wobbles very little across the generations. For Earth, this difference in axial tilt is roughly around 2.5 degrees only. But a more extreme example of this is planet Mars, where the axial tilt can be as far as 60 degrees, which affects the climatic changes on Mars quite dramatically. And so having a relatively large and massive moon and also relatively close to the planet is really important. Early on in the existence of Earth, for example, the moon was much closer, so the actual effects were much more dramatic as well. And so in this case, a moon that's size and mass of, for example, Titan, the moon of Saturn, orbiting slightly closer than our own moon, will allow this planet to be a lot more habitable for much longer periods of time because of the climate stabilization. The other advantage to having more habitability that was discovered in this paper was in regards to the size and mass of the planet. Here's actually how these two compare. This is a better Earth. Because it's about 10% bigger in terms of size than the Earth on the left, it essentially creates more surface area for life to survive on. At the same time, because it's more massive, it will retain more atmosphere with time, while the higher gravity will also allow this planet to retain a lot more heat on the inside. Because maintaining the geothermal heat as well as maintaining all kinds of activity on the inside is crucial for these planets to maintain life for a very long period of time. In terms of the temperature, they believe that about 5 degrees warmer on average than planet Earth would also allow this planet to have more diversity and better conditions. And specifically, the example they make here is the tropics on planet Earth. The tropics and the warmer climates on our planet have a much higher variety of different types of life, in comparison to, of course, some of the northern and southern regions, like for example the Arctic. In that sense, they believe that if a planet is on average about 5 degrees warmer, it will have more chance for life to evolve and to thrive in these warmer conditions. And this also includes the atmosphere. They believe that if the atmosphere contains about 25% to 30% oxygen, with the rest being nitrogen or some other inert gas, it will create slightly better conditions as well, as opposed to Earth right now where the oxygen is only around 20%. Lastly, it's also important to have plate tectonics for the planet to exchange all sorts of materials with the atmosphere. And lastly, a lot of different types of bodies of water and islands for life to evolve both in the water and on land. And so using these features and using the catalogs we have from various telescopes, including some of the planets that haven't really been confirmed yet, they've identified 24 candidates, with many of these planets still being candidates, meaning that we're not entirely sure if they're there or not. But if they are there, they would make a pretty good super-habitable planet. Now, 2 of these planets have already been confirmed, specifically a planet known as Kepler 1126b and another one known as Kepler 69c. Although unfortunately none of these planets have all of the features previously mentioned, meaning that maybe they're a little bit more habitable than planet Earth, but not necessarily super habitable to the point where they're the best planets we've discovered so far. And of all of the planets they looked at, of these 24 planets, only 9 of them were orbiting a K-type star, 16 planets were over a few billion years old, meaning that they were old enough to maintain necessary conditions, but only 5 of these planets had necessary temperature conditions, and that's of course very important. And also, unfortunately, every single one of them was really far away, over 100 light years away from planet Earth, with one planet specifically, and that's Kepler 69c again, being over 2,000 light years away. So in that sense, even if it is super habitable, doesn't really help us very much. But there was one planet that was very exciting. The planet orbiting the right star, the planet that seems to possess the right mass and size, and the planet that also might have the right temperatures as well. The planet whose designation you see right here. Now it's known as KOI because it's a Kepler object of interest. It's not a confirmed planet, it's a candidate. But assuming that this planet is real and assuming that everything we know about it is correct, this could be the first ever super habitable planet we've ever discovered. Although one major side note that the scientists make about this planet is of course in regards to its atmosphere. If its atmosphere is very thick, and if its atmosphere contains a lot of greenhouse gases, it might still be an extremely hot planet. But assuming that it has the right atmosphere, it could be an extremely interesting discovery. A discovery of a planet that's even more habitable than planet Earth. Although another important side note here is that just because this planet is super habitable doesn't mean it's going to have alien life on it. As a matter of fact, we don't even know what causes planets to evolve life until we discover life somewhere else out there. But it's still an important discovery in regards to trying to find another planet similar to planet Earth somewhere out there, or better even, planet that's even better than Earth. Which in contrast makes these planets extremely different, pretty much on the opposite side of the spectrum, from the extreme planets we've been discovering everywhere else, such as this planet right here known as Kelet 9b, that has some of the hottest temperatures in the galaxy with some of the most extreme conditions, the least friendly planet to life. But whether the planet known as KOI 5715 is an actual planet, and whether this planet is super habitable, will probably take us a few years to answer. We're going to need new telescopes, we're going to need more observations, and we're definitely going to need a lot more data from here in the solar system, specifically from Venus and Mars, to try to find out what happens to other planets and if life can evolve in other conditions as well. Which also means that it's actually pretty exciting times for space sciences and for various other discoveries we'll be making in the next decade or so. There have actually been quite a lot of versions of the so-called Drake equation in the last few decades, and a lot of them do come up with very different results. But most of the time the results suggest that there should be actual civilizations around us, or at least somewhere in the galaxy. But every once in a while we do have to rework the equation simply because we collect more data in regards to various exoplanets out there. As of 2020 we've discovered over 4,000 different exoplanets, and we now have a pretty good picture of how many different types of planets there are, and also what kind of stars usually have these terrestrial planets, and how many of these stars do often have terrestrial planets in the habitable zone of their planet. And using a lot of the modern data, the scientists behind this paper proposed that there should be around 36 different so-called CETIs, communicating extraterrestrial intelligences in the Milky Way galaxy. But why do they think so? How did they come up with this? And most importantly, why can't we hear them? A lot of their ideas are based on the modern understanding of the galactic formation and the formation of stars in different galaxies. Most importantly, it involves the idea of metallicity. Metallicity in astronomy refers to, well, pretty much everything except for hydrogen and helium. Hydrogen and helium are non-metals, whereas everything else is considered to be metals. It's a very strange name, but that's kind of how it works. The thing is, today we know that planetary formation depends on metallicity. The more metallic the star is, the more likely it's going to have terrestrial planets and even other planets orbiting around it. Stars that are low in metallicity will either have gas giants or might not even have any planets at all. And when it comes to metallicity in galaxies, today we even have this term known as the galactic habitable zone. Essentially, in a typical galaxy, we think that the inner part of the galaxy is not really habitable. First of all, it has low metallicity. Second of all, it's usually very active and has a lot of different flares going on, usually from the black hole itself. And most of the stars on the outskirts are the only areas where we can actually possibly find terrestrial planets capable of supporting life. So in order for us to find life somewhere, we need to be looking at areas of high metallicity and probably away from the black hole itself. All of this kind of comes into consideration when trying to work out this new Drake equation, the 2020 edition of Drake equation. And for this particular study, they took what we know about planet Earth to try to discover similar other locations somewhere in the galaxy where obviously similar conditions could lead to other life, similar to the one we have on Earth. In other words, they are looking at stars that are about 5 billion years old, or anywhere from 4 to 5 billion years old, and they're also looking at stars where habitable zones and metallicity are very similar to the ones in our own solar system. So basically, what the scientists behind this paper are trying to discover are the replicas of the solar system in our own galaxy. But there are actually a few more important features in this new formula that weren't really present in other ones. One of them is in regards to how long it takes for life to evolve on a similar planet, and here they try to keep it very similar to planet Earth. But the other one is in regards to how long a civilization can last. Basically, how long it takes for a civilization to survive and to stay technologically advanced before potentially going extinct. And this is really the important part here, because the scientists behind this paper make a very important assumption that it's very likely that many civilizations do go extinct. But before they go extinct, they make an assumption that an average civilization will have at least 100 years of communication using very similar devices to what we have here, or basically electromagnetic communication, using radio waves to communicate with the rest of the world, and of course the rest of the galaxy. So in other words, they make assumption that somewhere out there are similar species to humans that are trying to reach out and are trying to search for extraterrestrial intelligence, living on planets very similar to planet Earth, around stars similar to our own sun. And one of their more strict assumptions here is that their planet has to be about 4.5 to 5.5 billion years old, and they're also in a very similar stage of advancement and in a very similar stage of their intelligence to humans. So if we take all of these numbers into consideration, we actually come up with a number that's about 36, with the lowest number being 4, the highest being over 200. And if all of them are equally distributed across the galaxy, this also means that the nearest such civilization to us is going to be at a distance of about 17,000 light years away, with the closest distance potentially being 7,000 light years. And this is of course where we have our resolution of the Fermi paradox. First of all, the number of active communicating civilizations will directly depend on how long they're able to communicate for. If on average a civilization is only able to send radio signals for about 100 years, we will probably find an average of about 36 active civilizations in the galaxy right now. However, if it's, let's say, 1,000 years, this number will go up to a few thousand civilizations. So this really depends on how long the civilization is capable of, well, essentially surviving. And this is kind of where we also come to a very important conclusion from all of this. Because we don't seem to detect anything right now, it suggests two things. Either that, well, basically we're alone, or that civilizations don't seem to survive for a very long time. They don't seem to survive long enough to transmit messages for really long periods of time. Because we're not finding any active civilizations in our galaxy right now, it's a really bad sign. It just means that we might not really have a long-term existence in this galaxy. And so this could actually indicate our eventual fate as a species, as an intelligent, communicating species able to create these messages that travel across really vast distances. However, it doesn't mean that we're going to be going extinct anytime soon. Even according to the most optimistic calculations here, the closest such communicating extraterrestrial intelligence to us would be about 1,030 light years away from us. This is the best case scenario. That's actually double the distance to the famous Betelgeuse. And if so, that also means that it will take us about 2,000 years or so to establish an active two-way communication. And that's just not practical right now. However, for this best case scenario, if the average life of a typical civilization is less than 1,030 years, the average separation between stars becomes much too great for any communication to actually happen. In other words, the neighboring civilizations will never be aware of each other before going extinct. And one of the major explanations here is that, well, maybe if a civilization develops the technology to communicate over really large distances, it's also kind of related to technology that can also then sort of extinguish the species itself. In this case, what you're looking at right here, the rocket, was originally an ICBM. It was meant to be a destructive tool that would cause huge nuclear explosions across very vast distances, and it's really lucky for us that we were able to develop this destructive technology and create something useful out of it, and maybe some other civilizations were not as lucky. Maybe they actually ended up destroying themselves completely. But this is basically just one of the many explanations for why civilizations that develop communication might also be able to accidentally destroy themselves. And so this so far suggests that even though it's very unlikely that there are these really long-living civilizations that communicate for many thousands and even millions of years, it's quite likely, or it's quite possible, that civilizations with much shorter civilizational lifespan might be all over the place. There could be up to 1,000 of them in our galaxy alone. But the assumption here is that life develops always the same. It's always very similar to how it developed on Earth, and it also always leads to the same advanced civilization that wants to communicate with the rest of the galaxy. These are really big assumptions. We don't really know if that's true. And even though technically a civilization can extend its life by moving to another planet, like for example, if we as humans somehow manage to move to Mars one day, we might be able to extend our existence a little bit as well. At least that's the assumption here. But the scientists in this paper speculate that even this might not really prolong the existence of a civilization long enough for the interstellar communication to occur and for one of the civilizations to be able to hear another. So the resolution to the Fermi paradox here is that we're just really far away from one another. And just to give you a comparison here, over the last few decades, the entire SETI search has only scratched the surface here. If we were to consider the entire galaxy to be the oceans of planet Earth, over the past few decades we've only seen the equivalent of this tiny tank of about 8,000 liters. So basically, we have only sneaked a peek at the entire galaxy. We've barely seen anything and we've barely had time to look around us. And this is mostly because of the limits of the speed of light. But I guess the saddest discovery in this particular paper is that, well, it seems like unless we manage to survive for thousands and thousands of years and be able to communicate for so long, it's unlikely that we're ever going to hear anyone, at least mathematically speaking. In other words, this paper suggests that search for extraterrestrial intelligence will very likely fail. But nevertheless, there are a few really interesting discoveries in this paper that are sort of promising. For example, the scientists in this paper suggest that there could be tens or even hundreds of billions of different planets that do have primitive life, or life that's not really trying to communicate with anything, but just trying to survive somewhere out there. And we do have a very high chance of finding it if we keep looking, and also if we try to become an interstellar species and land somewhere out there on another planet. At the same time, they suggest that the peak of life in the galaxy, or basically when there was most civilizations out there that were able to communicate, was roughly around 5 billion years ago. In other words, we currently live in the times when there's actually a decline of these active civilizations, and it's probably going to be following even more in the future. So essentially, we could be one of the later species out there, assuming of course that all of the life everywhere forms in a very similar way. They also calculate that we would need approximately 3060 years to discover any extraterrestrial intelligence using a program similar to SETI, and the same would be true for other civilizations as well. So basically, if there are species out there looking for others, it would take them roughly around 3000 years to discover someone else out there. And to be able to communicate with them, they would probably need even more. But one of the more important discoveries here is that, let's just say that we don't discover any extraterrestrial intelligence within about 7,000 light years away from us. This is a really important discovery because it means one of two things. It implies that the lifetime of a typical communicating civilization is less than 2000 years. We've only started doing this, so ours is only about 100 years, so we do have at least 1900 years to go. However, that also means that at some point we might be able to go extinct, as many other civilizations have done so in the past. But the second assumption here is that life on Earth, and life in general, is just extremely rare, and life on Earth is indeed unique and does not automatically form on other similar objects. This is a really important assumption as well, because right now we don't really know if life is even possible on other objects, other moons, other planets. And discovering it somewhere out there might definitely give us a hint on what's going to happen in the next few thousands of years. In other words, this search for extraterrestrial intelligence is actually sort of like us trying to determine what's going to happen to ourselves in the next few hundreds and thousands of years. Are we going to be able to survive this, or are we going to go extinct like dinosaurs? And this of course also implies that the so-called Type 3 life, or artificial life that was created by the original creators, might also not exist. So even though some of us do dream of living forever and possibly even transferring our intelligence into something else and thus prolonging our lives indefinitely, it might not actually be possible, assuming that this is what everyone else does in the galaxy, because once again there doesn't seem to be anyone out there. And if these unusual species, these immortal robots existed, then we'd definitely hear at least a few of them trying to communicate with someone. And that's unfortunately not what we've been seeing so far. And so even though this paper does suggest that our search will eventually fail and that we're not going to be able to find anyone, and also that there's a big chance that we might not also survive ourselves, it is in a sense a very important message. It's a message that we need to be aware of our own existence and aware of the potential for our own demise. It's really important for us to understand that if this is indeed what's happening around the galaxy, there might be a chance for at least one civilization to prevent its own disappearance. And this could be us. Maybe we could be the first civilization out there to outlive our own potential destruction and to become, basically, the first ever Type 3 life. Civilization that does last for a very, very long time. But right now, all of this is of course just speculations based on mathematics and based on our observations of lack of everyone or anyone out there. So what seems to be like a century ago, or technically several decades ago, we've discovered this unusual planet known as 51 Pegasi b. This was essentially the first planet ever discovered around a sun-like star, and back then it was a huge achievement. It was discovered using what's known as radial velocity method, and we've already discovered several hundred planets this way as well. So the way that this method works is essentially by looking at how the star itself slightly wobbles around its, well, technically middle of space, middle of nowhere. If you look at the star and you sort of start noticing slight wobbling observations, and those observations seem to be periodical, it means that something is in orbit around it. But obviously, because stars are so far away and they're also kind of bright, it's almost impossible to see the actual motion, the actual wobble. So what we are looking for here are what you see right here on the bottom, the red shifting and the blue shifting effects. If once looking at the star you notice that once in a while the light seems to be a little bit blue shifted, or becomes a little bit more blue or higher in frequency, while at the same time then changing to redshift, and all of this happens periodically, there's only one explanation to all of this. Something is causing the star to move a little bit toward us and a little bit away from us. That something is usually a massive planet. And by using the first such observation back in 1995, the so-called LOD spectrograph was able to discover the incredible 51 Pegasi b. As you can probably imagine, in the last 25 years since then, we've dramatically improved this technique and made it at least 10 times more accurate. In other words, even though back then we could only see observations of basically equivalent to several meters per second of change in velocity, today we can easily see centimeters per second. That also means that we can detect much smaller planets, and we can do so with a lot more accuracy as well. The most famous such detector is also named after my favorite drink, espresso. European Space Agency has a very detailed explanation to how all of this works, but the thing is, it's sort of beyond the scope of this video. In a nutshell, it works exactly the same way. It looks at the blue shifts and the red shifts from a typical star, and basically uses these two cameras to try to see how much a star wobbles, how frequently does it happen, and also then uses all of this data to estimate what sort of a planet is orbiting around this particular star. Now, originally, this is pretty much how we discovered Proxima b to begin with. Proxima b around Proxima Centauri does not actually pass in front of its star. In other words, it doesn't cover the star because it's in a different plane of orbit, and so we can't really see the shadow of the planet. But we can, however, detect these slight motions, the wobbles of Proxima Centauri. And this is how Proxima b was discovered, and this is also how we discovered its much more massive, much bigger partner, Proxima Centauri c. So both planets were discovered using this method. The thing is, we're not really particularly sure, 100% sure, if these objects exist. They're still technically just candidates. And the recent confirmation from Espresso now almost certainly clarifies that this object here, Proxima Centauri b, exists. And it also seems to be even more Earth-like than we originally thought. Original values for its mass put it around 1.3 masses of planet Earth, making it about 30% more massive. Turns out that it's a lot less massive. It's about 1.17 masses of planet Earth, meaning that it's extremely Earth-like. And don't forget, this particular planet is also in the middle of the habitable zone of Proxima Centauri. So in other words, if by some unknown chance this planet has actual ice on the surface, water ice, which in this particular simulation it doesn't, but in this simulation it kind of does, it will definitely have liquid water on the surface, or at least very likely. Currently, the way it stands, we think that this is maybe one of the most likely prospects for us to ever find Earth 2.0, or at least closest planet to us that seems to be Earth-like. And it also has a really high chance to have a lot of other really exciting things on the surface. But there are obviously two problems with all of this. Problem number one is that it probably looks something like this if it has water. It's an eyeball planet. It's always tidally locked to the parent star unless it received some sort of a major collision with time, and also unless it has some unusual effects from its liquid ocean, kind of like what Venus had, to make it spin even slower, which is actually not good for any kind of life trying to survive here. We want this object to spin a little bit faster than it currently is. Currently, a single day here is equal to a single year here, which is about just over 11.1 days. Or technically closer to 11.2 days. What all of this means is that it always has this side exposed to the star, making it more likely to be hotter and also possibly having liquid water here, and also has these other regions that are known as twilight area, where there might be some potential for finding life here. The dark side is obviously just pure ice. The new version of Universe Sandbox has actually become really good at trying to simulate all of this. So here, if I were to sort of tidally lock a typical planet that looks like Earth in the beginning, it will quite quickly start transforming into the eyeball planet, and within only equivalent of basically several years of this star system, which is only a few hundred days in real time, it will sort of look like this. You have the eyeball, and then you have the ice on the dark side. Now, the interesting thing about this is that here we can also see the overall temperature across the planet, and in the middle of the planet, right here, it's pretty toasty, equivalent to a typical conditions in, I guess, a desert in the middle of the day. Whereas on the dark side is, I guess, not as bad. It's only about minus 11 degrees Celsius, which is, well, equivalent to a typical winter night in Canada. Although it does get colder in the pole regions up to about minus 90 degrees Celsius, so the pole regions here are really cold. So in that sense, these eyeball planets are pretty interesting, but definitely unusual. Now that's the first part about this planet that's different from Earth. The other part is, of course, the star. Currently, all of the observations of Proxima Centauri star suggest to us that it is what's known as a flare star. It flares up quite a lot, and you're going to see this as soon as I start running this at slightly faster than usual speed. You're about to see a flare coming out from the star, and it's going to be massive. And here you go, here's one of these flares. These flares are extremely powerful. They produce a huge amount of radiation that will most likely strip the planet of any potential atmosphere or possibly even liquid water, assuming of course it doesn't have magnetosphere or some way to protect itself. At least that's the current understanding of this. We still don't really know exactly what effects this might have on the actual planet. The other thing about this is that it also produces about 400 times more X-ray radiation, suggesting that the planet is probably irradiated by this extremely powerful radiation a lot more than planet Earth. So there are a lot of things with Proxima b that create these conditions that might be difficult for life to try to survive on this planet. So that's kind of our current understanding, and the confirmation of the existence of this planet and also that its mass is even more Earth-like make this even more exciting. So currently it's a really super cool planet. But there is something else coming from the study that scientists didn't really expect to find. It's still not confirmed, but there might be a third planet here, and it might be really small. This second planet, that we can now kind of refer to as Proxima d, is much closer to the star. Its orbit is around 5.15 days, or basically around twice as fast as Proxima Centauri b, and in this case, assuming of course this planet is also tidally locked to the star and is at a distance where it's currently located, it's really hot here, at least on the side facing the star. So if we were to look at the temperatures created in this particular region, this right here is somewhat similar to the temperature on the surface of Venus, over 400 degrees Celsius. The dark side is still going to be cold, actually much colder than the other planet because here it doesn't seem to have any atmosphere, and we think it probably doesn't, but overall this is going to be a pretty extreme world. So what we think we know about it so far is that it's maybe about 30% or around 29% the mass of our planet Earth. So in other words, it's more massive than Mercury and Mars, but it's less massive than Earth itself. Here's how all of these planets compare to this. So Mercury is here, Mars, Earth, and then this is the newly discovered Proxima Centauri d. And we obviously don't really know much else about it. And also this is still a very preliminary discovery. It still hasn't been confirmed by anything else or any other observations, and we need to have at least 2 more observations before we can claim this as an actual discovered planet. But since in general Espresso has so far been really accurate in its detections, I'm going to go on a limb here and say that it probably is there and it's definitely going to be confirmed. The current limits of Espresso allow it to measure planets up to about the 10th mass of our own planet Earth, so this is definitely within its limits. And assuming that this planet indeed exists, this would also make this the smallest ever planet discovered using this particular method, which is a huge achievement considering the fact that the first planet discovered was really massive. Here we're talking about just tiny minute observations of slight changes in the motion of a typical star. Just to give you a comparison to how, for example, the orbit of planet Earth influences the motion of our own sun, here in this graph you can see that the sun increases its velocity by roughly around 18 centimeters per second, depending of course on the position of Earth around its orbit. Which obviously means that Espresso located on another planet could have easily seen the motion of Earth around the sun as well. If we were some sort of alien species using Espresso-like device on another planet far away, looking onto the sun and trying to see if it has any planets. So this is how much accuracy we have now, and it's absolutely mind-blowing. And don't forget, this is also improving pretty much every year, so within a few years we'll be able to detect really tiny planets around many different stars. But since this is the first such paper exploring the system using Espresso, it will take time before we can confirm this. Until future discoveries, or until we discover something else around Proxima Centauri, that's all I wanted to mention in this video. It's definitely a really exciting discovery. Not only is Proxima b more Earth-like than we originally imagined it to be, it also seems to have another partner much smaller, much closer to the star. All of this is super exciting because this is our closest neighbor, and this is probably the first ever system we will ever be able to visit, assuming of course we visit anything. And since all of these discoveries have only been made roughly within the last 5 years or so, imagine what we're going to discover in the system in the next 5 years. It's going to be super fun. I'm not saying it's aliens, but it's not aliens. Hello wonderful person, this is Anton, and today I really wanted to talk about this recent announcement / press release that actually doesn't have a scientific paper attached to it just yet, but the papers are coming out. All of this is based on a story that came out in The Guardian And it's also based on what seems to be a leak from the actual scientists themselves, or possibly from one of the researchers that just couldn't hold it. The idea here is that we may have detected yet another unusual signal coming from an extremely close exoplanetary system to us. The system we're looking at right here, Proxima Centauri, the system that has the nearest terrestrial planet in the habitable zone. And this signal is very reminiscent of the 1977 signal known as the Wow signal that is even today not particularly understood very well because we haven't really been able to detect it again. In other words, what I wanted to talk about today is a potential detection of maybe a technosignature, but most likely something that actually came from planet Earth, but we just couldn't identify what it is just yet. And the reason this is so exciting is because it's coming from the world's biggest technosignature investigation project known as Breakthrough Listen, the incredible project that was started 5 years ago by some really prominent people. And the idea here was to essentially fund as many possible listening hours on various radio telescopes as possible. But obviously in our search for extraterrestrial intelligence somewhere out there, we've already discovered a lot of potential signals that were later on found to be nothing more but signals from planet Earth. Or even signals from a common microwave, the signal that was known as the periton that I discussed in one of the previous videos. And so what exactly makes this particular detection special, and why are we even talking about it? Unfortunately, until the papers come out, we're not going to know the details just yet, but from what we've already been told, this signal is specifically interesting for, well, 3 main reasons. Reason number 1 is its location. It seems to be coming from Proxima Centauri, because when the scientists were looking at a different location slightly away from Proxima Centauri, the signal disappeared. We know that Proxima Centauri's system is extremely interesting. Despite this being a red dwarf, it contains at least one planet in the habitable zone, the planet we refer to as Proxima b, and it does contain another planet known as Proxima c that's much farther away from the star and most likely is some sort of a frozen terrestrial world. Or maybe some sort of a frozen ice giant. Either way, there are at least 2 planets here, but possibly even 3. And at a distance of 4.26 light years away from us, this is as close as it gets. So having a planet in a habitable zone and so close to us is always exciting for us. And so back in 2019, scientists were using this beautiful Australian observatory known as the Parkes Observatory, actually one of the most famous radio telescopes out there, to try to investigate potential emissions coming from the planet simply because they were studying the ridiculously powerful flares coming from the Proxima Centauri star in order for us to really understand how this affects the planets. So by studying the radio signals from the flares, we might be able to get an idea of how powerful these flares are and how likely the planet might actually still have, for example, atmosphere and water. But luckily for us, or I guess surprisingly for us, one of the signals coming from the system was very similar to what we normally detect from planet Earth when it comes to basically just technosignatures, signatures of technology. So for example, compared to, let's say, a fast radio burst, which was also a mysterious signal that we're still kind of trying to solve, where normally you'll see several different frequencies in the signal itself, and various FRBs will have different frequencies. What's unusual about this particular signal from Proxima Centauri is that it seems to be similar to a single tone of a single frequency of exactly 982 MHz, or actually 982.002 MHz. And that's extremely precise and doesn't seem to change or modulate in any way. In other words, the signal doesn't seem to contain any information, but it does seem to be unnaturally flat, unnaturally constant, that is, which currently just does not have any explanation. Now, before we continue though, quick clarification. Normally, and this is what actually happened to a lot of these signals that were detected in the past, in most cases, these signals turn out to be, for example, flying satellites right above the point where we're looking at, and in many cases, these are either radio communication satellites, or in some cases, military satellites that have some sort of a secret technology on board. But in this particular case, the frequency doesn't seem to be associated with anything that we currently have in space, unless of course it is some sort of a maybe secret Chinese satellite for all we know. At the same time, because these satellite dishes are so sensitive, even a tiny radio transmission from somewhere nearby could actually accidentally produce these fake signals. This has happened many times before, and at the moment this is still a possibility. It just at this point nobody knows what exactly could have produced this specific signal. But because the signature of the signal is extremely similar to what we normally produce here on planet Earth, it seems to be, well, unnatural, in the sense that it's produced by some sort of a technology, maybe. We just cannot make an assumption yet that it actually came from Proxima Centauri, simply because there's still a chance it was basically maybe captured by something that was passing overhead, or something that was nearby, very close to the satellite dish. Now, the press release does mention that at least 4 signals were detected, but some may have been just radio interference, and this was over a period of several days. So if there was something hanging over this area, for example in outer space, it could have been maybe a geostationary object. But at this point we don't really know, and we cannot really assume this, because when they tried to look at this location very recently, nothing was actually discovered there. So if it was an actual signal coming from, for example, space, from maybe a satellite that was there, it may have shifted locations and is most likely not there anymore. And if by some unusual chance this was a signal coming from Proxima Centauri, which is a big if, in this case someone just turned it off. It's no longer emitting anything anymore. But once again, this is a really big if, and very likely is going to be proven in the next few years to be something most likely artificial, made by humans, and that was just emitting the signals in this particular frequency. Now, just for fun, I actually tried to look up if anything that we know does emit 982 MHz, and except for this particular study that investigates these very unique lasers that are used in communication that do emit frequency by essentially blinking the lasers at frequency of about 982 MHz, there was really nothing else I discovered. And these particular lasers also have a very unique application in essentially fiber communication. I'm not entirely sure if there is some sort of a fiber that might have been causing this, maybe some sort of a cable connection close to the satellite dish, but for all we know, this could have been actually one of the possible explanations. Because if you remember, 5 years ago, the explanation for the so-called periton signals was the microwave oven that was actually located not so far from the Parkes Observatory. So the previous unknown radio signals from this observatory were nothing more but someone just opening microwave oven a little bit too soon. But the reason so many scientists are going to be very eagerly awaiting these scientific papers to come out is really because even when there is a tiny possibility that it is aliens, everyone is going to try to investigate this, simply because a lot of our science really depends on this, depends on discovering extraterrestrial intelligence somewhere out there. But in all of the previous attempts, so far it's been just something very easily explainable, such as, for example, pulsars. And for all we know, maybe this particular discovery will actually lead to a discovery of a new phenomenon we've never known existed around various exoplanets before. But that's not all. There's actually something else that was really interesting about this discovery, coming from the tiny pieces of information that were thrown to us by whoever leaked the information to begin with. So it turns out that the signal itself was also slightly blue shifted, or essentially its frequency was increasing a little bit, suggesting that it was moving toward the planet Earth. Or at least that's just one of the implications. It just means that the signal is moving closer to us because the frequency is going up. Now, this blue shifting is very well understood, so we can actually figure out how fast it's moving, but until the papers come out, we're not going to be able to know anything about it. And also, unless we actually see the signal again, and unless we're able to somehow detect it from exactly the same location as we found it before, we're not going to be able to confirm this as a technosignature or any kind of an interesting alien signature. It's just going to remain as a potential disturbance from something else terrestrial that we just couldn't figure out. Now, like I said before, 982 MHz is not a very well-used frequency. It's not something we normally use on Earth, but it could also be just someone's broken radio, someone's cell phone not functioning properly, or a plethora of other things that do produce radio frequencies in that specific way, especially because we know in the past very similar signals have been detected and already discredited as something that was basically produced by a device on planet Earth. Nevertheless, the signal has officially been given the designation BLC1, which stands for Breakthrough Listen Candidate 1, because this is the first time we've ever found a signal that has sort of passed all of the other filters. It's exciting enough for us to do a lot of follow-up studies and to try to discover what actually produced this after all. Now, probably not aliens, but at this point, I'm sure a lot of scientists are going to put a lot of research into this to find out who truly did it and what actually caused this. But I guess for now, I'm not really going to speculate any more about this, because there's just nothing else I know except for what you can read in the amazing article written by actually it's the daughter of Frank Drake, Nadia Drake, who wrote a pretty good article about this that I'm leaving in the description below. But the main researcher doing all of this is this wonderful person, Sonia Sheikh, who I'm sure is going to release the paper about all of this sometime soon. And hopefully really soon, because a lot of us are so excited to see what actually was discovered back in April and May of 2019. Because that's when the original signals were detected and we've just identified them very recently. But until we learn more and until those papers come out, that is unfortunately all I have for you. It's a pretty exciting announcement, it's definitely something really interesting, reminiscent of 1977, and it's something that many scientists will be very eager to learn about and to study in the upcoming months. Hello wonderful person, this is Anton, and today we're going to be talking about a discovery of a very interesting rogue planet, or a planet that doesn't actually have any stars or anything it's connected to, that's traveling across our galaxy and seems to resemble planet Earth, at least in terms of mass. So let's discuss this new discovery in a little bit more detail, and let's start with just a general explanation of what these rogue planets could be and how they're created. Generally speaking, some planets can be created completely by themselves without a star. In other words, they can be actually formed in the middle of the galaxy from the primordial gas and just never really get enough weight to be stars. But some planets, and we think that this is one of these planets, are created a little bit differently. Imagine that this is an early solar system where various types of early planets and also various types of material orbits around the Sun itself. Notice how within only a few hours of the creation of the system, a few of these planets already got kicked out through the gravitational interaction with other objects. And there's of course a lot of other stuff like collisions with the star, collisions with planets, and so on. But overall, within only a few years of running this simulation, I'm going to lose a pretty large percentage of these planets. And today, most studies suggest that about 70% of all of these stars in the galaxy probably go through the loss of these planets through various unusual means, such as this right here that's known as planet-planet scattering. And eventually, if we wait long enough, up to about 50% of the planets will actually escape this solar system, this star system, with one right there moving really fast, as you can see. And the less massive the planet is, the more likely it's going to escape, assuming that it approaches some sort of a massive planet in the vicinity. And in our own solar system, we believe that Jupiter and most likely Saturn were both responsible for kicking out a lot of smaller planets, including one major one, sometime in the past. And so obviously this is just one of the other ways that these rogue planets can be generated, because once these planets escape, they start traveling across the galaxy, and most likely spend the remainder of their existence just traveling completely by themselves through the emptiness of space. And the closest such object is only about 6 light years away from us, and it's one of the closest extraterrestrial or extrasolar system objects that we've discovered so far, and it's essentially a type of brown dwarf that's very difficult to see unless you look at it in infrared light. And the majority of studies today also suggest that up to about 1 trillion, if not more, of these rogue planets probably exist in the Milky Way galaxy, and they definitely outnumber all of the stars in the galaxy. So these rogue planets are all over the place. But seeing them is another story. Trying to find them, trying to pinpoint where they're located is extremely difficult. They produce no light. This one is an exception because it's a brown dwarf. Here's a much more realistic representation of this. This is essentially what they would look like. There's nothing here. Complete darkness. Which of course also means that these are extremely mysterious objects. But we do have ways to find them. And one such way is using an extremely interesting Polish telescopic survey known as OGLE, that stands for Optical Gravitational Lensing Experiment, and uses this telescope you see on the screen that's located in Chile. The telescope itself has only one purpose. Its purpose is to look into the night skies for a very long time and to try to discover gravitational lensing effects. Essentially, it's looking for this. The effects coming from some sort of a massive object passing in front of another object and causing that object to create a gravitational lens. Normally we see these coming from different galaxies and different galactic clusters, but once in a while we get lucky and see them because of a star or even a massive planet. OGLE has already discovered several major planets, but a lot of these planets so far have been pretty massive. But this time the story is a little bit different. This time, by reanalyzing the data from around 2016, the scientists were able to spot a gravitational lensing effect that you can also find in the paper in the description below, that essentially lasted for something like 45 minutes, or closer to even 42 minutes, and was also extremely small in its magnitude. But even though it was small, it was definitely detected and it was definitely there. And with gravitational lensing effects, the longer they last and the more magnitude they produce, the more massive the body is. So if something happens really fast, and if something happens with very small magnitude, it means that whatever passed in front of the bright object was probably not massive at all. In this case, the mass of this object is estimated to be anywhere from about 30% to 100% the mass of our own planet, meaning that this was a terrestrial planet that we've detected. And this particular planet would pretty much be one of the smallest and the least massive objects we've ever discovered using this method, while at the same time being the only terrestrial rogue planet we've found so far, assuming of course it is a planet. For all we know, this could be something completely different. It could be some sort of a chunk of dark matter. It could also be some other exotic but compact object, but right now the chances of it being anything but the planet are very low, because we believe there are many planets out there, and because we believe so many of these planets are spread across the galaxy. The most likely, and I guess the easiest explanation in this case, would be that this was indeed a rogue planet kicked out from some star system somewhere out there that we were now able to see with this telescope. But I guess the other question is, are we certain that this is a gravitational lensing effect? Because technically it's really tiny. And it's also really short. Could this have been something else? Like, for example, a flare from an active star, which apparently this was. OGLE telescope was actually looking at a relatively active star, and in this case it could technically be something completely different. And at the same time, because this was such a short event, only a few data points were collected from this event, with only about 15 data points being certain, and you can sort of see them right here. However, is this enough? Normally, in science at least, we expect a lot more data before we can definitively say that something has happened. And in this case, it's a pretty valid criticism to make an assumption that maybe this wasn't really a gravitational lens, but something else. But one thing that the scientists mention in this paper that makes them believe that this was an Earth-like planet and this was a gravitational lens was the actual shape of the event that you see right here. Because we've observed so many different gravitational lenses over the past few decades, and because we've collected so much data, we can normally tell when a gravitational lens occurs simply based on the actual shape of the data, which in this case looks almost identical to what we normally expect to detect when gravitational lenses occur. So in that sense, it's more likely that this was actually an Earth-like object in terms of mass, and this was a rogue planet, but we don't really know how far away it was. We also have no idea what it might contain, what it's made out of, what its composition is, and the saddest part is that we also will probably never be able to see it ever again. Normally, gravitational lensing effects of the same object are extremely rare. We expect a planet to produce one maybe every few 100,000 years, maybe even every 1 million years, but definitely not within our lifetimes. So it's very unfortunate that we're probably never going to know anything about this planet or ever see it again. So in that sense, it was an interesting discovery, but unfortunately we're not really going to learn much about it. The scientists behind the paper, you can find in the description, decided to try to create simulations and identify some of the smallest and the least massive halos of dark matter that the universe could have produced. And the main reason they wanted to do this is to try to identify the actual origins and of course the composition of the dark matter itself. So let's discuss this in more detail and discover what the scientists found as well. Now, first of all, this right here is essentially the nutshell of what the scientists were able to create. By using extremely complex supercomputers, they were able to simulate a virtual universe, and then they were also able to zoom into very small parts of the simulation and discover what the really small parts of the dark matter would look like, assuming of course the simulation here created relatively realistic representation of the dark matter. Although right now we don't really know how accurate this is. But the physics it's based on and the understanding of the universe is based on is pretty much spot on. But normally when I talk about dark matter, or whenever there is a new video about discoveries regarding dark matter, there is still a little bit of skepticism from people that might not actually think it's real. Well, I wanted to actually address this because it's really important to understand why a lot of physicists and a lot of scientists today believe that dark matter is the best explanation. Now, I'm not going to go into the details about the observational evidence because there's quite a lot of it and most of it points at the existence of dark matter, if not all of it. I'm going to talk about the actual particle reasons we believe that dark matter exists. Specifically in regards to various discoveries coming from particle accelerators around the planet, most of which came from the Swiss CERN particle accelerator. Now, surprisingly, here in Google Earth you can even go on a tiny tour and go inside of CERN, discovering what all of this looks like on the inside as well. If you do have some free time, I encourage you to check this out because it actually looks pretty awesome. But anyway, the idea here is that over the past few decades, CERN discovered some really incredible things about various particles that technically could be created somewhere in the universe. And the more we discover how many different particles could be technically created in extreme cases of the universe, the more we realize that there are just so many different opportunities for dark matter to exist, simply because there are so many different particles that could explain its existence. Now, all of the matter we're familiar with here on planet Earth, for the most part, can be summarized in these two familiar states. But in reality, in the last few decades, we started to discover a lot of really unusual states. Some of them, such as tetra quarks, can actually create a lot of different particles, many of which could have properties that could easily explain what the mysterious dark matter could be made out of and how it could affect the rest of the universe. But as we make more and more discoveries, the physicists started to realize that there are currently just way too many possibilities. So many, as a matter of fact, that it's somewhat difficult to look for the actual dark matter itself. In other words, it's become somewhat impossible to pinpoint what exactly dark matter could be made out of. There are currently way too many candidates and not enough experiments trying to test each of the candidates. And all of these experiments are usually pretty expensive. So what we've discovered from CERN and from other particle accelerators in the last few years and in the last few decades, more and more seems to suggest that dark matter could be some sort of a really exotic particle after all. Possibly even something that we could eventually create inside a particle accelerator. On top of that, every single simulation of the so-called universe in a box, essentially when you try to take a supercomputer and recreate the universe itself by using various parameters and basically create what we would observe somewhere out there in space, do continuously reinforce the idea of dark matter being completely real. But because the dark matter itself seems to be really difficult to pinpoint, most of the modern studies decided to focus on trying to simulate these universes and then really zoom into the maximum amount to try to see what they can discover on the inside. And what you're seeing on the screen is, as of today, the best possible visualization of what very small halos of dark matter might look like. Every single tiny circle you see, that's essentially tiny pieces of dark matter roughly around mass of planet Earth, all of which form these very long tunnel-like structures that then form even larger structures that eventually form the extremely long and very large cosmic web, inside of which each of the galaxies then starts forming with time. And on top of that, every observation we make of the universe seems to reinforce these ideas even more. There really doesn't seem to be a better explanation. Which also of course suggests that whatever the scientists discovered very recently by zooming into the dark matter might also make a lot of sense. And what the scientists in this paper once again confirmed is that, well, first of all, the galaxies and also various stars and various clusters all started forming inside of these very massive, very large cosmic formations, but all of these formations were initially created by the dark matter. So basically, before the first star was born, before the first galaxies were created, this already started to exist. And although the biggest of these structures would contain galactic clusters, really large and very massive structures, the smallest ones could contain things like solar systems and star clusters. In other words, even these smaller tendrils that you see right here, which are also dark matter, would actually contain various star objects, various planetary objects, and in some sense all of this suggests that right now we're also inside of a kind of a smaller dark halo bubble. Now surprisingly, the levels of zoom they were able to achieve here, or the level of detail they were able to see, is somewhat equivalent to looking at the moon from Earth and seeing a tiny insect on the surface. And you can actually see how much they were able to zoom in by looking at one of the illustrations in the paper in the description below. And eventually you'll notice that the zoom itself reaches the cross-section of roughly around 80 light years across, which is the highest and most detailed level we've ever been able to achieve so far. And so assuming the simulations in this paper are correct, this would mean that somewhere along this little hallway that you see right here, you would have a larger chunk of dark matter where the solar system would be located as well, and Earth itself would also be orbiting inside of this little halo of dark matter. But most importantly, other stars would also find themselves along this hallway. And for all we know, one day we might be able to find a way to navigate these dark matter hallways and possibly move across space slightly more efficiently than what we can do right now. Although currently this would be the realm of science fiction, not really actual science. But by identifying the existence of these different types of halos and also by knowing the actual parameters and of course the structure of these halos, we might actually get a better chance of confirming their existence and of course what they're made out of. Because the scientists behind this paper and many other papers believe that these dark matter particles will actually collide with their antiparticles and create all sorts of different radiation that we can technically detect from planet Earth. And more specifically, it's actually a type of a gamma ray radiation that upon detection can only mean dark matter. In the past there have been similar detections from the outskirts of the galaxy, we've never really found it from somewhere nearby. So if these smaller halos exist as well, we should technically be able to discover some of the more unusual gamma ray radiation coming from very close in the vicinity of planet Earth. But in order to detect this, our current telescopes need to be recalibrated to become more sensitive. But the scientists also suggest that some of these halos might be really small and not massive enough to contain anything inside of them and could be actually completely by themselves alone somewhere out there in the galaxy. And if suddenly we look at the night skies and discover an unusual patch of gamma ray lights that seem to match the prediction from this paper, it could only mean that we might have detected one of these smaller halos, the ones that are too small to contain anything on the inside. And so the major discovery coming out of this paper is that maybe this is actually what the universe looks like. It's smaller bubbles inside the larger bubbles inside the largest bubbles, which are also connected to one another through these very long cosmic streams. But this is where predictions sort of end because we don't really know which particle is responsible for producing dark matter, and depending on the particle and depending on what type of an exotic particle it is, it could also be producing some other unusual observations. But one of the other surprising discoveries in this paper is the structure of dark matter itself. It seems that no matter how much mass you give to dark matter, whether it's a big halo or a much smaller one, it seems to have a very similar structure in general. It always seems to have a lot of density on the inside, with density decreasing as you move away from the center. So even though the size and the mass of the halo might be different, even if it's really small or really large, the structure seems to be for the most part the same. And these tiny halos are just as important as the larger ones, simply because their sheer number seems to add up to a really large portion of the total dark matter mass, which implies that instead of trying to discover very large dark halos far away from Earth, we should really try to focus on finding much smaller pieces much closer to our own planet. Although that still means that we need much more sensitive and much more precise gamma ray telescopes pointed at various locations in the night skies. But all of these new studies and all of these new simulations and discoveries take us a few steps closer to finally discovering what this unusual matter is, and most importantly, trying to find out how one day we could possibly use this to help humanity. Just like a lot of other discoveries in particle physics and a lot of discoveries in astronomy, this might not really make sense to us right now, how and why this is important. But just like every other discovery related to space sciences that eventually led to the invention of, for example, MRI or cell phones, at some point all of these discoveries in regards to dark matter might end up creating something absolutely mind-blowing. But for now, we're just going to keep looking, keep trying to find out what exactly it is, and if it's for some reason something that we just didn't understand about the universe, it will still help us improve our understanding and various technologies that we currently use for a lot of other studies as well. So in the last few years, we've discovered quite a lot of various exoplanets, and one of the main reasons for the new telescope known as TESS, that orbits around our planet Earth and looks at every region for about 27 days every single time, essentially is to try to discover as many habitable planets around our planet, very close to the solar system, as it possibly can. Now, in the last few years, it already has discovered several potential targets. We usually refer to them as TOI, or TESS Object of Interest, and in many of these cases, these planets were somewhat exciting, but not entirely, as you would call them, habitable. Basically, many planets discovered so far are interesting, but we probably would not find habitable conditions around many of these objects. One of the more exciting findings that we talked about last year was this right here, TOI 270, which had a few interesting planets. But now we've discovered something even more exciting. Just as exciting as the TRAPPIST-1 system that was announced a few years ago. So essentially, this new system known as TOI 700 was discovered to have 3 exoplanets passing in front of the main star by looking at this for about 11 months. And it was recently confirmed with another telescope known as Spitzer telescope that you can see right here that's about to end its mission. So essentially this discovery and this confirmation was one of the last things that it's going to do, and actually one of the greatest ones as well. But what's interesting about these 3 planets discovered and confirmed is that they seem to be all very Earth-like. But on top of that, at least one of them is exceptionally Earth-like and is located in the so-called habitable zone, where we do expect to have liquid water. Now, there's only a handful of exoplanets we've discovered so far that do potentially possess ability to maintain liquid water, and this now is one of them. Now let's actually go and try to recreate some of these planetary parameters by using the Universe Sandbox. So first of all, the star itself, known as TOI 700, is what's known as a red dwarf. So basically it's an M-type star. Now these are normally not particularly hospitable to, well, anything really. A lot of these so-called red dwarfs are often what we call flare stars. The best example of the nearest flare star to us is actually the nearest star to us, Proxima Centauri. You might remember a few years ago we identified this planet known as Proxima b, the closest exoplanet to us that also seems to be in the habitable zone of the star known as Proxima Centauri. But the problem with this star system is that the star Proxima Centauri is what's known as a flare star. It essentially flares up and releases a tremendous amount of energy very, very frequently. So frequently, as a matter of fact, that all of the analysis we did so far suggests that this would strip the planet of any kind of atmosphere and possibly most of it, or even all of its water, basically making the planet a barren world with nothing on the surface. This is obviously very unfortunate, but it's also kind of how Mars lost its atmosphere as well, except that our sun is not a flare star, but even in our own solar system, the solar effects can be quite profound. So we usually try to identify M-type stars that are not flare stars, the ones that don't produce these powerful flares. The ones that can't really strip the planets of atmosphere and water. And in the 11 months of observation of TOI 700, the scientists have not seen a single flare. So there might be some good news here. Now, usually M-type stars kind of lose this flare ability once they get much older, so maybe this is just a much older star system. Maybe this used to be a flare star system, we just don't really know yet. We've only identified this very recently. But then we have these 3 planets, and just from looking at them, you're not going to be able to actually see what's going on here because we haven't really analyzed them in thorough detail. So instead I created a very rough model of what this might be like. So first of all, these 3 planets are all somewhat different, and the closest one here is very similar in size to Earth. Here's Earth for comparison. The problem is that this planet is also much closer to the parent star and receives just as much radiation as Mercury does. So in that sense, it's very likely a very, very hot world, unless it has some strange atmosphere that prevents that from happening. But in terms of mass and in terms of size, it's extremely similar to our own planet. In that sense, it's probably very similar in density as well. We do need to investigate this a little bit more, but for now, it does have very unusual Earth-like properties. The second planet, Planet C, is very different. It's very likely some sort of a gas object, or possibly something similar to a super-Earth, because both the size and the mass of this planet are much larger than planet Earth, but the density here is much lower. So this might be some sort of a super-Earth, or possibly a mini Neptune-like object. We're not entirely sure yet, but it's probably also extremely hot because it is once again much closer to the star, and in some sense it receives just as much radiation as Venus. So this could be technically what's known as a super-Venus, basically a Venus-like object, a lot of thick atmosphere, a lot of heat, and a lot of radiation here, but also not really exciting for prospects of life and liquid water. And so really it's this last object here, known as TOI 700d, that seems to be located on the outskirts of the so-called habitable zone where liquid water could technically exist, that gives us the most promise. So once again, this is just a simulation. We don't really know what this object might look like. We do, however, suspect that this object is tidally locked like every other planet around M-type stars. In other words, this is what we call the eyeball planet. It's always facing with the same side toward the star, allowing one side to become really hot, other side to become probably somewhat cold, and having this really unusual twilight region right here, where there might be quite a lot of hospitable places for humans to survive, or even other life to develop. In comparison to Earth, this object is just a little bit more massive and a little bit larger, but this does suggest that its density is very Earth-like, and it might even contain very similar materials to what Earth contains. At the moment, more studies are needed to both identify the atmosphere and the composition of this planet, but for now, the suggestion is that it's basically one of the most Earth-like objects identified so far, and is definitely the most Earth-like planet that TESS was able to find in the last few months, or basically since it started operating. So it's a very exciting object. It's definitely one of the most exciting planets discovered in the last few years, and it will probably have a lot of follow-up studies identifying what's happening here. But to help identify specifically what's happening on this planet, NASA has actually created at least 20 different models of what type of an object this might be. For example, they simulated what this object would produce in terms of the light coming off it if this was what's known as an ocean-covered early Mars, basically a Mars-like planet that contains Mars-like features and produces light patterns from its atmosphere similar to what early Mars would produce. At the same time, they tried to create a model simulating what a modern Earth-like planet would look like if it was in this position. And most importantly, the scientists identified the light emissions that would be created by these types of planets if a certain type of atmosphere and a certain type of composition was present on this type of a planet. These models are actually meant for us to use other telescopes like James Webb Telescope that's going to be launched in 2021 to look at them again and to try to identify the signatures that the atmosphere might produce in order for us to see what's really happening on the surface and of course in the atmosphere of these various planets. Now, at a distance of about 100 light years away from our planet, it's obviously not an object we're going to be visiting anytime soon, but being able to identify these planets for potential future exploration of humanity is really important for us. However, one thing is definitely certain about this planet. Whether it's an eyeball planet or some other unusual Mars-like planet that we've never seen before, it is definitely going to be extremely different from anything here on planet Earth. It is not going to be an Earth-like planet in the sense that it's an Earth replica. It might have habitable conditions, but because its star is so different from our own sun, and because basically the star system here is also very unique, it's going to be different in many different ways compared to planet Earth. In the last 10 years or so, we've discovered a lot of really unusual planets. One of such unusual planets is right here. This is known as Konrad 20b. This was one of the densest planets ever discovered, and it sort of, back then and even now, defied our understanding of how planets formed. In other words, it doesn't really make sense that this planet can exist with the properties that it currently has. The major problem with this planet is that, despite its size being relatively similar to Jupiter, its mass is higher than Jupiter, meaning that it has a lot more density. The density here is even more than the density on Earth, suggesting that this unusual gas giant is not really as gassy as some of the other planets that we know of. But in terms of discovering these so-called hot Jupiters, there are still a lot of mysteries that we don't really understand about them. However, there are even rarer planets out there, the type of planets we currently refer to as hot Neptunes. In other words, they are smaller, they're less massive, they're more similar to Neptune and Uranus, but they're also extremely close to the parent star, giving them extremely hot temperatures. These planets are quite rare, and especially when we look around the galaxy and discover other planets in this region. Turns out there is something known as Neptunian desert. Essentially, planets with a mass of several masses of Earth, but less massive than Jupiter, at these really close distances to the stars, are extremely rare. The first such discovery of NGTS 4b a few years ago made the headlines because it was an extremely rare planet in this location. But now the scientists discovered something even more rare. Another unusual Neptunian planet, but this time with extremely high density, at least for a gas giant. The planet currently known as TOI 849b, discovered by the TESS telescope, seems to raise more questions than answer them. Located over 700 light years away from us, it's somewhat difficult to actually analyze this in detail, but we know that this planet orbits around its star every 18 hours. The star itself is also extremely similar to our own Sun, and so the temperatures on the surface here are somewhere around 1800 degrees Kelvin or about 2000 degrees Celsius. Its mass, however, is much higher than Neptune. It's about 39 masses of planet Earth, whereas Neptune is only about 17 masses of planet Earth. But in terms of the size, it's relatively similar to Neptune, which means that its density is much higher. It has a density of about 5.2 grams per centimeter cube, which is a little bit less than our beautiful planet Earth. And this is a big deal because planet Earth is already one of the densest objects in the solar system, and it's definitely the densest planet in the solar system, mostly due to the extremely large, very massive and also very dense metallic core inside our planet. Now, we believe that gas giants also have cores, but because we don't really know how big and how massive they are, we never really had a chance to study them. But since this unusual object seems to be very dense and seems to be size of a typical smaller gas giant, the only reasonable explanation to what we're seeing here is that we actually are looking at an exposed core of a potentially failed gas giant or a gas giant that was slowly destroyed over time. And although this is not the most massive Neptune planet we've discovered, this is also not the densest planet we've discovered, so far this is one of the rarest because of the combination of different factors. First being the location, known as the Neptunian desert, second being the density of this planet, and third being the fact that we can't really explain how this object was created and what it truly represents. Because technically speaking, this is the most massive terrestrial object we've discovered so far. It's not just a super-Earth, it's more of an ultra-Earth. Its mass is close to 40 masses of planet Earth, meaning that the gravitational attraction on the surface here is at least 3 times higher. And normally these extremely massive, extremely large planets are expected to have very large hydrogen and helium atmospheres. Basically, all of the gas giants in our own solar system eventually accreted really large envelopes of gas as they were orbiting around early solar system. So the fact that this planet doesn't seem to have this really large, unusual hydrogen and helium envelope is a mystery right now. And there are currently 2 major explanations to what may have happened. It could have been a large gas giant before, but with time a lot of this gas evaporated and essentially escaped into the outer star system. However, today we believe that this process actually takes much longer, so technically this planet should still be a lot more massive than it currently is. The other explanation here is that maybe this planet got gravitationally disrupted by the star itself, and a lot of its gas escaped through the tidal interactions with the star or possibly some other planet, thus leaving only the core behind. So that's one possible explanation here. But the other explanation relates to the idea of the planetary formation and just the gas present in the early star system. Here, the scientists believe that maybe this planet just never really got to absorb just as much gas as some of the other objects. And although initially it may have had a lot more mass, eventually as it migrated closer and closer to the star itself, even though some planets do end up inflating and receiving even more gas from some of the other objects, This planet for some reason started to lose its gas over time, thus remaining as a kind of an undeveloped or underdeveloped core of a potential gas giant. In other words, after a few million years, once this planet moved to this location, it more or less stabilized, stopped losing its mass, and eventually just became a remnant core of a gas giant that never really got to be a gas giant. In other words, this could be the first ever core of a gas giant that we actually can study in detail now. And because this is something we've been wanting to do in our own solar system for a very long time, but we're simply unable to do because there's no way for us to see inside Jupiter, Saturn, or other gas giants, here we might finally get our opportunity by literally looking at the core of a planet that never really got to be a true gas giant. But because it's still kind of far away, it's over 700 light years away from us, even looking and seeing this planet is still somewhat difficult. So studying this core is a bit of a challenge. Although somewhat related to that, here in our own solar system, we believe that at least one object, the asteroid known as Psyche that you see right here, is also a core of an underdeveloped planet. Not a gas giant, just a regular planet like Earth, Mercury, Mars, and Venus. And in 2026, NASA is planning to launch this spacecraft to try to go and investigate Psyche, and then essentially take the first ever direct look at an actual core of a planet that could have been. So by studying this planet and also by studying Psyche, we might be able to understand cores of planets and possibly even discover something we currently can't even imagine. But the thing is, in this particular case, the planet still has a little bit of an envelope. Approximately 4% of the total mass is still hydrogen and helium, meaning that some of the planet is still unfortunately covered in the atmosphere. So we don't really truly see the core itself, we see the core with a thin layer of atmosphere. In that sense though, it truly makes TOI 849b the most massive terrestrial planet we've ever discovered. It seems to possess atmosphere, it seems to possess the conditions very similar to Earth in terms of density, but it has very high gravity, obviously ridiculously hot conditions, and at the same time is also probably evaporating its atmosphere and losing its atmosphere to the rest of the star system, meaning that at some point it will truly become a core, but just not anytime soon. And because of its terrestrial nature, the scientists behind this paper also believe that it might possess other volatiles, including water, in its atmosphere. But because of the temperatures here, all of this is extremely hot. But this doesn't mean that similar planets do not exist in other regions of similar stars. So we actually can expect to one day discover a somewhat similar planet, but somewhere on the outskirts of the star system, possibly even in the habitable zone of the star, suggesting that we might one day find what seems to be the biggest Earth-like planet ever. A planet that could possess thick atmosphere, very large, possibly even global ocean, and potentially be the largest habitable world we'll ever discover. So just the fact that TOI 849b exists means that there are more similar planets somewhere out there as well. And in case you were wondering how they were able to discover both the size and the mass of this planet, it actually used two different observations. The first observation from TESS used the so-called transit method to see the shadow of the planet as it passed in front of the star. This is how we were able to determine the size of this planet. Then, by using the radial velocity method and the apparatus known as HARPS, the scientists were able to see by how much the planet was causing the star to wobble in its orbit. These observations show us the Doppler effects, the blue shifting and the red shifting of the light coming from the star, and thus we can then determine the mass of this planet. And then using the mass and the size, we can calculate the density of the planet. And in this case, they discovered that it was about 39 masses of planet Earth, but had a size of slightly smaller than Neptune, suggesting that its density was very similar to planet Earth, thus making it a terrestrial planet. But because this is a relatively recent discovery, we don't unfortunately know anything else about the object, its origins, or really anything else about the star system. I'm sure in some of the future studies we'll discover something else about this, but for now, that's unfortunately it. Thank you for watching, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something you may have not known before. Also, maybe support this channel on Patreon, it does help me quite a lot. And alternatively, you can also support this channel by buying the Wonderful Person t-shirt you can also find in the description below. I'll see you tomorrow, space out, and as always, bye bye.